Možete. Aha. Ne možemo baš svako drugo. Ja sam vakcinisana. Znači, mi smo do 11:30. Imamo 3 plenarne. Evo, 2 plenarne. Profesor Filip Kokan, je li ovdje ili će biti online?
Online, svi su online predavači, da.
Pritiska ili ne?
Ne pritiskajte.
Možemo da počnemo?
Mora da se uključite.
Okay. Good morning, everybody. Welcome to our today morning session. Today we have 2 plenary lecture and 1 presentation. The first plenary lecture is Professor Filip Kokaj from the University of Maribor, Faculty of Mechanical Engineering from Maribor, Slovenia. And the title of his presentation is Waste to Energy in the Light of Circular Economy and the EU Waste Management Plans. Please, if you can put his biography.
Thank you. Dr. Filip Kokaj is employed at the University of Maribor, Faculty of Mechanical Engineering as assistant professor. He graduated over 20 years ago in the field of power engineering, preparing a simulation tool for diesel engines operation based on experimental data. In the year 2002, he finished his master's studies, and in 2006, doctoral studies in the field of environmental engineering, focusing on computational fluid mechanics, modeling a solid waste combustion. Graduation and post-graduation studies were done at the University of Maribor, Faculty of Mechanical Engineering. In the past, he worked for several years as a designer and a project manager at a private company producing solid fuel, fired steam, and hot water boilers and waste incinerators. During that time, he was the head of the project and the main designer of the first Slovenian municipal solid waste to energy plant. Since the year 2000, he has been the co-worker at the Laboratory for Thermodynamics, Combustion and Environmental Engineering at the Faculty of Mechanical Engineering. He has many references in experimental and numerical research and design of waste to energy plants. There are numerous references in combustion modeling using computational fluid dynamics, experimental laboratory and pilot scale technology testing, developing waste treatment methods and applying various waste management concepts. He was also the head of performance tests of small wood-fired boilers in terms of efficiency and air emissions for the Slovenian National Ecology Body. He is also involved in renewable energy and efficient energy utilization projects on application level at public company Energetika Maribor. He is the author and co-author of more than 450 technical and science papers in the fields of mechanical engineering and environmental engineering. More than 15 of them are original research papers published in high-impact international papers. He also co-authored 3 books. The research work is mostly done with close international collaboration. For more than 10 years, he has been a member of the Slovenian Chamber of Engineers and authorized mechanical engineer for designing, building, and supervision for pretentious buildings. He was a fellowship holder of ZOI Slovenian National Scholarship for more gifted pupils and students in the period between 1988 and 1999. He took part at Combustion Summer School at Princeton University, USA in June 2012. Since 2018, he has been the president of the Regional Energy Council and at the Styria Chamber of Commerce and member of the supervisory boards in public entities. Dr. Kocher. Dr. Kocher?
Yes, good morning, ladies and gentlemen. I will take over now. I first have to thank the organizers for inviting me to this conference and letting me do this presentation, this plenary session. So basically, I would really love to be with you at Jahorina Mountain today, but due to pandemic, I couldn't come. That's why I'm doing this online. I will right now share with you. I hope that you all see now share. Okay, I believe that you now see the presentation. Yes, you do. Okay. So basically, I will talk to you about waste to energy connected to circular economy that is being going on for over 5 years in European Union, and of course about European waste management plans in the future. The outlook of the presentation, basically after the introduction, I will give you some ideas regarding sustainable development that is closely connected to circular economy. Ideas will tell you the connection between the circular economy and the waste management, and of course present you the status of waste to energy in European Union now, what is the future of waste to energy, and of course within 30 minutes I will try to conclude this presentation. What are the global issues? In 20th century, the growth of population was by a factor 3.7. The use of natural resources, when it comes to materials, it grew by a factor of 34. We were extracting ores and minerals by a factor of 27. We were using fossil fuels. The growth was by a factor of 12. And also the increased use of biomass by a factor of 3.6. So the total material extraction grew in the 20th century by a factor of 8, and greenhouse gas emissions grew by a factor of 13. And also we had, up to this pandemic, big globalization that was taking place. So all of these issues do influence our environment enormously. Near future, by 2050, of course, this was the estimation before the pandemic, the population should grow to a number of almost 10 billion. And also what is really big concern is that the estimation is that around 3 billion people will move from low to middle class, and also the consumption will rise. If we take a look at just recent data that were published a year ago by OECD. Also, despite all the efforts, we will see enormous increase of use of materials in next 40 years. When it comes to global level, the United Nations have prepared so-called SDGs, or Sustainable Development Goals. All of you working in the field of environmental engineering are surely aware of them. For all the rest of the people listening today, I would really recommend having a look at those documents. They're really good written with good ideas. They're on a global level. So they include really good ideas on all those fields presented in this slide. Let's come back from the global level to Europe. What are actually our European challenges? As you already know, Europe imports more natural resources than it exports. When it comes to natural resources, we can say that Europe as a continent is rather poor. Of course, because of this high amount of imports, Europe is very vulnerable to volatile raw material prices, because everything is on a stock exchange. So if prices go up, then also the competitiveness of European industry goes down quite a lot. The other thing is that Europe still generates about 5 tons of waste per person per year on the average, and only little more than a third is effectively recycled. So there is a very big potential in terms of using the waste that we are producing right now. And the idea is to have Europe a secure, competitive, affordable, and sustainable sources of energy to provide it to the citizens. This year, European Commission published European Green Deal. This is actually an extension of circular economy package that was introduced in 2014. This circular economy package was originally introduced by a Slovenian commissioner, Professor Janez Potočnik, that introduced it to the European Union. So basically, with this European Green Deal, the Europe would like to transform into a modern, resource-efficient, and competitive economy where there will be no net emissions of greenhouse gases by the year 2050. The economic growth should be decoupled from resource use. I will talk about 2-3 slides later about this decoupling. And the idea is not to let any person or place behind. So everything should be decentralized within whole European Union. Of course, with this Green Deal, the European Union would like to boost the efficiency use of resources by moving to clean circular economy. So this is where the circular economy goes into this European Green Deal package, and restore biodiversity and cut pollution. This is a very nice chart of the material flow diagram in European Union. It's in gigatons. It's for the complete European Union, all 27 states that were in European Union in 2018. So basically, just have a look at this green line that is showing the recycling. As you can see, this recycling is still rather small compared to complete material flow that goes through European Union. And also you can see that imports are around 1/4 of all material flow through European Union are imports. I already said that one of the goals with this new European Green Deal package was so-called decoupling. What does that actually mean? This chart shows it all. The whole idea is to increase the human well-being. To increase human well-being in capitalism, of course, you need to increase the economic activity that should go up and up every year. But the economy, the society up till now functioned that if you wanted to increase the economic activity, you had to increase the use of resources. So the idea is to decouple these two activities. So to have the increase in economic activity, but not to use more resources. The same thing goes to environmental impact, because in the past, when you increase the economic activity, you also increase the environmental impact. And this has to decouple, so disconnect, so to say, these two influences and preserve human well-being and preserve the economic activity and, of course, save natural resources and lower the environmental impact. Let's go to circular economy. Of course, I will say throughout these presentations many times that circular economy is, of course, not waste management. Waste management is only small part of the circular economy as a whole, as a complete idea. But let's see what the circular economy should be. So the point one, it should preserve and enhance the natural capital of a region, of a country, of a continent, by controlling finite stocks and balancing renewable sources flows. So the second one is to optimize resource yields by circulating products, components, and materials at the highest utility at all times in both technical and biological cycles. And the third one is to foster the system effectiveness or efficiency by revealing and designing out negative externalities. Of course, it has to go, the circular economy has to go hand in hand with the energy union, with the climate, with the jobs, with economic growth and investment, and of course, with the social system in the country. So change democratic barriers and prepare better regulation or legislation in order to function this new circular economy approach. Some transition toward a circular economy. What we should do, of course, we should minimize waste generation. We should maintain products, material, and resources in the economy as long as possible. And these all should bring economic, social, and environmental gains. Because it's circular, there are always people like to show such figures with the circles. The whole idea is, let's go through all these ideas of the circles that are depicted here. On this first one, the idea is not to return the products to the front end completely. Maybe it's possible to return it only halfway and reuse it. So basically to find a way not to return it completely at the front end. If it's possible, lets the materials circle a bit more. This is by extending the lifetime of a product, of a material. When it comes to cascading, the idea is to reuse it for another product and another product and another product, and at the end, then put it, of course, back at the front end. Also, when it comes to pure imports, this is really, really important when it comes to waste management, not to include hazardous materials into the products, because when products become waste, and when one would like to recycle those waste, then of course you recycle materials that include hazardous materials, and these hazardous materials can then be included in new products, and of course they're unwanted in those new products. So European Union does a lot in order to exclude hazardous materials from the production of new materials. When it comes to circular economy, of course, you cannot bypass this Ellen MacArthur so-called butterfly. That is actually also showing these circles on right side. So these blue lines is about finite materials or finite sources. When it comes to the left side or the green side, these are the renewables. And these are some ideas how to use materials, how to use products in more sound way. So enhance maintenance, enhance reuse, refurbishment, and at the end it's recycling in order not to lose the materials. The same goes for the other side, how to stepwise use all the renewable materials. As I already said, waste management is only a small part of a circular economy, because when it was introduced in 2014, most of my colleagues working in the waste management field, they said, okay, yeah, this is advanced waste management that is going to take place now. Now the idea is much greater, but when it comes to waste management, the idea is to use the organic matter in the waste as a source of energy. Of course, in general, the matter or the materials in waste can be used in a material way, or reused or recycled in a material way, or the energy can be recovered from the waste. When it comes to municipal solid waste, it is a partially renewable energy source. And as you know, European Union has also big goals when it comes to renewable energy sources use, the end use of energy, and also there is a great potential to use the energy of the waste to produce electricity and to produce heat. And also, we would like to be a society without waste, so-called zero waste. Of course, we will never get there completely, but why not use the whole potential of the waste? This is something I like to show also to students. Circular economy is not waste recycling, is not modern waste management, is not a high-tech waste treatment. It's much more, but of course, waste management is included in circular economy ideas. How to get to the society with almost no waste that is going to be deposited off. We all know this pyramid of prevention, minimization, reuse, recycling, energy recovery, and disposal. The whole idea is to start with the reduced use of material and conserving the materials that we are already using. Of course, we should encourage cyclical use of resources and shift incentives to stop wasting materials. Then, of course, we should encourage manufacturers to design products for sustainability and take them back. This is done, of course, through the extended producer's responsibility that is getting bigger and bigger and bigger, and is going to be bigger and bigger in the next decade in European Union. Reuse some products that are not good for somebody can be still good for somebody else. Recycle and, of course, regulated disposal at the end. Let's go through some cycles and the ideas of circular economy when it comes to waste management. The one thing is clear. These ideas work on a closed territory. This is not something to be global. So basically, in your territory, in your region, in your city, one should create the possibilities for circulating materials, for reusing materials, for reusing products. Of course, this multi-R approach comes from the waste hierarchy. So reduce, reuse, recycle, these all should be applied also when it comes to circular economy. Of course, there is a great role of local and regional authorities, because if you want to change the economy, if you want to change the society, of course, the legislation and the governance need to follow these ideas. And of course, new business models will evolve to encourage this process. Just one more when it comes to circular economy and waste management. So basically, we are actually right now not in a linear economy anymore. We are somehow in a chain economy in this region. So basically, we are cycling a bit. But when it comes to real circular economy, then we will actually stop using new resources and producing waste. On a global level, how well developed we are in waste management. This is one picture that was prepared a little less than 10 years ago, but it shows a lot how efficient we are in Europe. We are producing around 540 kilos of municipal solid waste per year per capita. USA is producing 730 kilos per year. And in Europe, we, back then in 2012, recycled 43% of the waste, which is the biggest percentage. Then it was the USA with only 24%. And what can also seen here on this picture is that there are more than 500 waste-to-energy plants operating in Europe. There are 86 operating in the US, and also in China. Back then in 2012, there were 100 in operation and 200 being built. So when it comes to this waste-to-energy, again, Europe and also, not depicted in this picture, Japan and South Korea are the most developed countries and regions when it comes to waste-to-energy. If we take a look at the latest data of municipal solid waste management in European Union countries, you can see big difference among the countries. On the left side, you can see the Central and Northern European countries that are actually most developed countries when it comes to waste management. They are landfilling, this orange or red color, they are landfilling almost nothing, around 1% or little more than 1%. The rest is being utilized in waste energy or recycling and composting. So they're already using most of the waste. On the other side, there are more or less new countries that came at last to the European Union, like Bulgaria, Romania, and Malta. They're mostly landfilling everything, and they're recycling and composting only a little share of the municipal solid waste. This can all again be seen how things evolved in the European Union. Of course, the legislation was changing in this period from 2001 and 2015. So in these 15 years, the legislation was changed 2 times when it comes to waste management. And you can see that in these 15 years, the landfilling in general went down by 30%. Waste to energy went up 11%, and recycling went up by 18%. When it comes to my home country, Slovenia, we of course do have some difficulties when it comes to waste management, but also in recent years we were able to increase material recycling, composting, and digestion when it comes to municipal solid waste, also separate collection, and we were able to lower the amount of municipal solid waste that is being landfilled. When it comes to separate collection, of course, this chart says municipal waste recycling. This is something that was not written okay, because sometime in the past, some 5 years ago, Slovenians were the European champions when it comes to separate collection. But of course, the separate collection of municipal solid waste fractions is not already also recycling, because recycling is another process that takes place somewhere else. And if someone would take a good look at the statistic, one would see that only 1/3 of separately collected fractions is really recycled. The rest, unfortunately, not. Some slides about the legislation of waste management in European Union. Maybe you know, maybe you don't, that's why I'm showing it. So the first European directive on waste was published on July 15, 1975. So more than 45 years ago, there was the first European directive on waste, and it was published only on 3 pages. I encourage you all to have a look at this directive. You can find it on the internet. Why? Because already back then it included all ideas when it comes to waste management that we would like to implement even today. So back then, people were really, really smart. They prepared an excellent document, and as I already said, it is only on 3 pages, but it says it all. This text was copied directly from it. So basically, the states should encourage prevention, recycling, and processing of waste, the extraction of raw materials and possibly of energy therefrom, and any other process for the reuse of waste. So basically, the ideas that we are still trying to implement today, they were already almost 50 years back then written in the directive. So the encouragement, the reduction of quantities of certain waste, the treatment of waste for its recycling and reuse, the recovery of raw materials, and the production of energy from certain waste. it was all back then, more than 45 years ago. It's still in the latest general directive on waste that was recast, updated in 2018. So when it comes to waste legislation, there is a really good site of the European Commission regarding waste law. It's not only the directives, but also the summary of the directive. So everything is really good explained. So have a look at it. And let's see what the European Union, with this latest recast of the directives that was done in the summer of 2018, what they would like to achieve. There are some goals set within those directives. So there are different ones, not only general directive on waste, but also on landfilling and also on specific sorts of waste. So basically, when it comes to municipal waste recycling, the idea is that by the year 2025, the European Union as a whole, so all 26 states that remained in the European Union, should recycle at least 55%. This should rise to 60% by 2030 and to 65% by 2035. By January 1st, 2025, the separate collection of textiles and hazardous waste generated by households need to be established. And also a year earlier, also for bio-waste that is collected separately and completely recycled. When it comes to food generation, also the idea is we should produce 50% less food waste by 2030. When it comes to restrictions on landfilling, by 2030, all the waste suitable for recycling or other material or energy recovery is not allowed to be landfilled anymore. When it comes to municipal solid waste, by 2035, it is only going to be allowed 10% of mass to be landfilled. Very important thing is that the completely new rules were set for calculation, verification, and reporting of data on waste, because up until 2018, there were quite big differences among countries because everybody was using this statistical data in a different way. So this was then recast, these rules, and now they're much better. Let's see one stream, how should be put into a circular economy. You all know the ideas regarding plastic. When it comes to plastic materials, also in European Union, there is one estimation that still the use of plastic materials will in next 20 years increase by 100%. So we are going to use more and more plastic despite all the ideas of using less. This is on the left side, this is a status in 2013. And these are on the right side, the ideas how to reuse and recycle more plastic materials. When it comes to waste management, of course, I encourage you to visit this International Solid Waste Association site. There are really good ideas regarding waste management ideas in association with the circular economy. Okay, now we came to the main part. It's the waste to energy. So this WTE is waste to energy. The idea is to use the energy of the waste. There's some other acronyms used also. like energy from waste, so EFW, but basically all of them say the same. We should use the energy that is actually in the waste. This is not only incineration of the waste, also it could be used by combustion, by pyrolysis, by gasification, but there are some other possibilities to use the energy of the waste. One is the anaerobic digestion, so to digest the organic material and produce biogas and use this biogas as an energy source. But today I will focus on incineration and co-incineration processes with the following presentation. When it comes to, again, European policy, there is this statement that was prepared in 2017, and what it says that the waste to energy is a part of circular economy, because when circular economy was introduced in 2014 and 2015, some of the people thought, okay, this is the end of the waste to energy, because we are not going to burn the waste anymore. We are going to reuse it, recycle it completely. This is, of course, not true, and the European Union prepared this document. It's not a long one, like 17 pages long, and it says what actually the countries of the European Union should do regarding waste to energy. So these are some extracts of these documents. What they say that in waste to energy plants, only non-recyclable waste should be combusted or used or recovered. When it comes to capacity of the plants, there is a clear analysis that the Central and Northern Europe has overcapacity of plants. When it comes to Southern and Eastern Europe, there is undercapacity. And of course, if new plants should be built, they should be built in the southern part of European Union and eastern part of the European Union. This is again about the also regional distribution, I already explained. When it comes to technological level of plants, as you know, some countries have plants that are 50, 60, even 70 years old. They should be renewed, not also in the environmental sense, but also in technical sense to increase the efficiency of the energy production at those plants. Of course, the idea is to combine waste to energy plants with other sectors. Why? To increase the use of produced energy. So it's a need to connect waste to energy plants with other industry sectors that can use the steam or hot water, or to combine waste to energy sector with district heating systems. What's the amount of waste incinerated in European Union and the number of plants? You can see that this number is constantly increasing. Also the amount of waste incinerated, and also the number of plants that are operating in European Union. This is now the number of plants per country. The most plants has France. It has more than 120 plants. In Germany, there are 80 plants. In USA, of course, USA is not in European Union, but okay, it's depicted here. They have more than 80 plants around the USA. But for the rest of the European Union, there are between 10 and, let's say, 20, 30 plants per country. Italy has a little more than 50 plants. and let's see the average plant capacity. Why is this really important? Because in generally the size does matter when it comes to price of the waste treatment. But here one can see that in Finland they have average plant capacity less than 10 tons per hour. This means less than 80,000 tons of waste per year. And in Portugal, they have average plant size of over 70 tons per hour. In general, rule of thumb is that the waste to energy plant should be bigger than 50,000 tons per year. But of course, if it's really, really big, then also the price of the treatment goes a bit more down. But again, this is one part of the story, because if you have really, really big plants, you need to support the plant with the enough amount of waste, and you then increase the transportation cost and also the influence of the transportation on the environment. This is latest data on waste energy plants in 2018. As you can see, this is the latest data. In Germany right now are operating 96 plants. In Spain, in France, 121. So a country with really many waste incinerators compared to the population size is Switzerland, with 30 plants operating. And also
Professor Kokoy,
yeah.
because 45 minutes passed, but I please you to make conclusion.
Yes, I'll come to conclusions.
Thank you very much.
Yes, thank you. Okay, this is the energy from waste in European Union. What you can see here is that there is a great potential. Also increases of more than 50% when it comes to electricity. When it comes to heat use, it could be increased also quite a lot. This is some analysis done for the year 2035. Why? To look ahead for next 15 years, because the lifetime of a waste energy plant is at least 20 years, and also these projects cannot be built within 5 years. Some analysis like this were done also for Slovenia to see what amount of waste will need waste incineration. This is one analysis of waste to energy process in numbers, how things look like. I'm not going to go into details because of the time. All the engineers I will encourage to take a look at the European Union reference documents on best available techniques. There is a special section for the waste to energy, so waste incineration. And this document is completely new. It was released, the latest version, in December 2019. So if I come to conclusions, basically waste can be source of raw materials and or energy. With appropriate organization, a comprehensive waste management system in suitable installation is needed for today and tomorrow. We are not going to be without waste also tomorrow, so we'll need some kind of a waste management system. Of course, all the waste management should be done within legally permitted environmental impacts. When it comes to waste energy, electricity and heating or cooling can be achieved. Producing energy from waste means reducing greenhouse gas emissions. And the only thing that should be used by waste energy plant is the waste that can be recycled. Yeah, waste energy in circular economy means sustainable economic growth, sustainable industrialization, green jobs, and contribution to achieving sustainable management of natural resources and their effective utilization. Thank you. That was all from my side.
Thank you very much, Professor Kokel. Unfortunately, we don't have time for the questions, but
Okay.
if you have questions, you can write in the chat. Thank you once again.
Okay.
Our next plenary lecture is Professor Dejan Popović from the Serbian Academy of Science and Arts from Belgrade, Serbia. The title of his lecture is Where the Engineering Meets the Nature, External Control of Sensory Motor System with Disability.
Sorry, I will start again. Professor Dejan B. Popović, retired professor of biomedical engineering, School of Electrical Engineering, Belgrade, the member of the Serbian Academy of Sciences and Arts, Belgrade, Serbia, foreign member of the Slovenian Academy of Sciences and Arts, Ljubljana, Slovenia, member of the Academy of Engineering Sciences, AINS, Belgrade, Serbia. He is professor emeritus at Aalborg University, Aalborg, Denmark. He was professor for more than 40 years at the University of Belgrade. He was professor and senior researcher at the University of Alberta, Edmonton, Canada, the University of Miami, Florida, Miami Project to Cure Paralysis, and Aalborg University, Denmark. He published over 500 papers, several books and textbooks. He is the author of 8 patent applications. The Google Scholar data shows more than 8,100 citations and the DH index of 48. He was project leader of or participant on several NIH, NSF, NIDRR, and SERC projects. He was the project leader or participant in several FP6, FP7 EU projects. He led several Tempus projects related to the development of new curricula for master students. He was instrumental for the development of several startups in Denmark and Serbia. He was the associate editor of IEEE Trans on Neural Systems and Rehabilitation Engineering, Medical and Biological Engineering, Computing, a member of the review boards of Medical Engineering and Physics and Neuromodulation. He was the editor of Journal of Automatic Control, University of Belgrade. He was the chair or member of the scientific committees at more than 80 international and national meetings. His memberships include founding member of the International Functional Electrical Stimulation Society, fellow and founding member of the European Alliance for Medical and Biological Engineering, president of the Serbian Society for Electronics, Telecommunications, Computing, Automatics, and Nuclear Engineering, IEEE Institute of Electronic and Electric Engineers, EMBS Biomedical Engineering Society. Professor Popović. Professor Popović, are you with us? Unfortunately, these things can happen. Professor Popović, are you with us? Can you hear us? I'm sorry for these inconveniences. Unfortunately, these things can happen. Professor Popovic, are you with us? We can't hear you, Professor Popovic. Please stay with us and be patient. Sorry for the inconvenience. Of course, this is the normal thing to happen when online presentations are at stake. Professor Popovic? Ne može.
Can you hear me now?
Yes, we can. Professor Popovic,
Perfect.
you can now start.
I was
Sorry for the
I
inconvenience.
was not able to unmute myself. I mean, anyway, you can probably see me now. And what I need also is to share my screen. Can you see that?
Yes, we can.
Excellent. Thank you very much for inviting me to the meeting. And I was looking very much to actually participate on a beautiful mountain of Yahorina. But unfortunately, due to this situation, it was impossible. One of the things that I was missing in the previous lecture was actually how we will handle the waste of the masks that we have to wear. There's a zillion of masks that are thrown everywhere. This presentation. So and I will be talking about the things and problems that I am involved in through a long career that was described in many details. So what you see here is a movie, and this movie was recorded in 1963, so which is almost 60 years ago in Belgrade, and that's a very famous Belgrade hand that was developed. And that was something that triggered actually my attention when I was a high school student and brought me to this interesting field on what we can actually do and how the engineering can step in and assist people who have disabilities, being an amputation or paralysis or anything like that. And I was lucky enough to come in a group at the University of Belgrade and join the group also at the University of Ljubljana, which was the leader in another field. So to learn a lot about that and also to get integrated. Now, I will be talking specifically about something that is called neural prosthesis and how we can integrate the engineering research into something that can assist people who have disability. What is a disability? What's the motor deficit? If someone has a stroke, suffers a stroke, meaning that there's a problem with the brain, that can be whatever, but this brain doesn't send any more signals, and as a result of that, there would be a disability. One side of the body would be paralyzed, and that's called hemiplegia. In the case of a spinal cord injury, that means that there is an injury in this column here. There will be no communication between the brain and the periphery, and because of that, either the legs will be paralyzed or even the legs and arms will be paralyzed, like in the case of tetraplegia. That's not a very good image because the face and the head are not, should be in a health car. Anyway, with this, an ultimate way and something that can work very well is presented as something which a colleague and friend of mine, Grégoire Courtine, who is sharing his time between Lausanne and Geneva and several other places, is trying to do, and he is just joining the rest of the world in order to actually prevent disability. The best way will be to step into the central nervous system and assist the central nervous system to regenerate. There are many attempts so far to try to do that, but the nature is actually rejecting any implants that will actually do what is presented in this slide here. So at this point, it is impossible actually to cure the paralysis by connecting the neural network that is in the brain and the spinal cord and the peripheral lesion. Things that can be done are actually something else, and this is to assist either by stimulation of a central nervous system or periphery, how to deal with this. Some of these things are known for a long time. And the work actually started in Ljubljana, Slovenia by a group of professor and academician Vodovnik and academician Kralj, academician Bajd, and here is academic Kralj still being active in Ljubljana. And so what they developed and designed, they designed a method how you can put 2 electrodes and by sending bursts of electrical charge, extend the leg, and by sending the burst of electrical charge into the peroneal nerve here, flex the leg. So what you can do is you can control the leg movement, although it is paralyzed. So this person is paralyzed, and without electrical stimulation, which is right here, the person cannot stand. If you combine these 2 movements, like this, it is shown here, and note date, this was in 1984, what you can do actually, you can assist a person. So what I'm talking about integration of the engineering devices, just a generator of electrical bursts or pulses, very similar to what a pacemaker will do to the heart, but in a much more complex situation. Because in the heart, you have to generate 1 pulse per second, and that will assist the person to more or less live normally. In this case, you have to deliver a set of charges to several muscles in the body. And if you succeed to do that in a normal way, it might be possible to do other things. I was explaining how complicated this is. If you look into the list of muscles that are assisting the leg movements, extending the knee, flexing the hip, extending the hip, you see there's a long list. And what you see here, this is 1 gait cycle. So this is heel on the contact and heel on the contact. And these muscles are active, each of them in its own timing, and they have profiles. So this is higher activity, lower activity. And if you look into these muscles and do the simulation, what will happen is you will see that the body moves. However, with an external approach, you cannot access every muscle in the body like you would like to do. And as a result of that, you have to limit your model and to eliminate some of the muscles, so reduce from probably 30 or 40 muscles that are controlling 1 leg to reduce that to only 3 or 4 groups of muscles. And if you succeed to that, you may actually make someone stand and walk. Now, what we have to do is these 2 systems, electrical stimulation or an exoskeleton, like you will see in a second later, what they will do, they will move body segments, but they work in parallel with the natural biological control. In a biological control, the signals are starting from the brain, and then from the brain, they go from the brainstem, they come to the spinal cord. The spinal cord is distributing these signals to various muscle groups. It goes to the motor neurons, goes to muscles. So this here is something that we have to, what is missing in a spinal cord injury, it's either this is damaged or the spinal cord is damaged. So if you don't have these descending signals, you have to control everything on the periphery. So in order to do that, what you can use in engineering is to use artificial control. So by sensors, you can generate some information. You can then generate the control signals and actually more or less reproduce this here. In nature, the signals are going through nerves. In the artificial control, you activate the nerves by stimulation, by positioning the electrodes and sending bursts of pulse. So what this is altogether is, I'm showing here a video that was recorded in one of my studies many years ago, where we instrumented an experimental animal, a cat in this case. And what you see on the right are the signals that you can record from muscles while the cat is walking. And this can be done in other animals as well. It can be done in humans. So you see a burst of activity in several muscle groups. And if you also look into the kinematics, you can see what are the movements. So if you analyze these elements, then you can see how the nerve activity and muscle activity are connected. How is this important? So you see, you need the descending signal. This goes to the nerves and it goes to muscles. So what we see here is we see that some of the nerves are generating activity, and this activity then go into muscles. Now, if you use these signals and you try to reproduce something, and that's just showing one of the programs, and that's the MATLAB simulation of all of what you see. So you see with these red lines, these are muscles. So this here, the top graph, shows the simulation while you don't have really good control, and because of that, very fast, the 2 legs that are proposing. And on the bottom one, you see the simulation, you can test various protocols. So what we developed we develop simulations and we can control and pick up which muscles are active. In order to actually see how this works, you may observe this short video. So that's the simulation of a person. It looks like a cat, but it's basically almost the same as a person will be walking and using a walker or crutches. So the legs are supporting the movement and the arms are actually providing the balance. So you see, if you change the environment, so you increase the pressure, so more load on the back, then the muscles will have a harder time. The change of the color of the muscles on that simulation show periods when the muscles are active or non-active. So the red muscle that is dark is an active muscle, and the muscle that is pale is the muscle that is not active. So you can actually simulate this and do very much in analyzing and trying to develop an appropriate control, which is the biggest problem. How to integrate this external control to fit into the schema which exists in the natural control. So that in total, when you apply, ends up with this here. So after years of research, if you use sensors that are measuring the joint angles in the knee and the hip, and there's a sensor that is put into the shoe that measures the ground reaction force, the distribution of ground reaction force, and there is a stimulator, a person who is paralyzed from the waist down, paraplegia, can walk. And we had many of these patients working in several places in the world. But as you all can see, you never saw a person like that walking on the street. So that's still not good enough. So we have to do a lot, and there will be years before this actually starts to be really practical. Patients are not interested to have a system like that. Tuning the system like that is very complex, so things need to be greatly improved. This whole idea of using actually and bypassing the lesion is not new, and it doesn't come from my research. That's an image taken from the conference papers in 1967, a very famous conference, and it came from a group that is from Rancho Los Amigos, one of the biggest rehab centers in California, US. And what they suggested is if you have a voluntary command and there is a problem, so something is broken, so the signals are not coming to periphery, then what you have to do. So imagine that this graph was created and published in 1967. So that's what we want to do is actually, this is the engineering part. How we can record the signals coming from the brain, how we can process this in real time, how we can interface to the periphery, and can we actually integrate this all into what the person wants. So when you see what we can actually do this, there's a lot. So based on many other activities, we also built a system that can do the following. So that's a person who has a paralyzed arm. And by stimulation on 4 muscle groups, and this unit here, and in a timely activation, synchronous activation, the person can grab different objects. So this person without the stimulation cannot use the left arm at all. That's a hemiplegic individual. So the right arm is functioning normally. So this person can handle the controls that are built here. So this here is actually the stimulator generating 4 channels of electrical stimulation. These 4 channels are generating activity of 4 muscle groups that are in the arm, allowing the hand to open and close in the right timing, and thereby allow a person to operate various objects. And this system has been used, and there are commercial devices that are built on this, which is actually what we need in order to make. One of the problems when you use one of systems like that is a complexity of which muscle groups need to be stimulated and which nerves can be stimulated in real time. In order to do that, we built, and that follows the trend in the world, a system that has, instead of one big electrode on a hand, it has an array of electrodes. And this array of electrodes, when it's positioned on the arm, if you activate these specific fields, you're activating the nerves actually that are below that. In order to come to a map, what we did is we combined an interesting device, which was built by the company Embrain Train. That's a 24-channel recorder that records the activity, electrophysiological signals. It can be used to record activity from the brain, but it can be also used to record activity from the muscle. So when you do that, you see here 2 of these devices, and they are recording activity of the muscles opening the hand and closing the hand in a person with hemiplegia, and that's the hand which is not paralyzed. So we record also the movement. So here what we can do is we can actually establish which muscle groups are active in order to do that with an array of electrodes. So if you look into this through time, you can see what are the zones that actually need to be here activated in order to do something like that. So having this in mind, opening the hand goes through these sequences, and we can see that on the electrode, on one of the sides, you see an increased activity. And when you want to go into the next phase, what you have to do actually is, this is now applied on a paralyzed arm, and you will see it here in a second. This is for closing of the hand, a device that we built to measure the actual force that will be developed with that. These are not simple experiments. Now, this is a paralyzed arm. So now we stimulate with this layout that you see here. We activate the muscle with an array electrode. And as you can see here, there's basically very little movement that can be done. But this, through practice, will actually lead to a much better performance that you will see here. Now, this is a paralyzed arm. You turn on the stimulation, and there's an opening of the hand. So what we can do is, by applying engineering methods, record the normal activity, activate the specific activity, and get the movement that we want. A company that has a unit in Belgrade, which is called Tecnalia, they're located, and their center is in San Sebastian, Spain. And this device was developed in Belgrade, Tecnalia Belgrade. And that's actually a device that shows an industrial version, so to say, of what you've seen before. So that's an array electrode, and with this array electrode that is connected remotely to a computer, a therapist will select which fields need to be activated, and then a person can grasp various objects. This is a typical ball grasp, and obviously open the hand, and in that way function in the society. The good thing of electrical stimulation, especially applied in stroke individuals, is that when using that, there is a therapeutic effect. This therapeutic effect means that the person, after an application, like 3 weeks or 4 weeks or 5 weeks, he can stop using a device, and the movement will be memorized in the preserved structures of the brain, so this person can function without it. It doesn't work in all patients, but it does work in many patients. Studies that we did with more than 300 individuals in various rehab centers across Europe show that there is a positive effect in a large majority of stroke patients if you apply it at the right time, and that is in a very acute phase, almost immediately after a stroke. Now, in order to improve that further, and that's the best that exists at this point, is the development of implantable systems, so not a surface electrodes. At a center in Cleveland, Ohio, that's Case Western Reserve University, led by the group of Hunter Peckham, who is now retired but still active in this. They built a completely implantable device which uses the electrode that are shown here. So all the parts and pieces are here. That's the stimulator that works here. That's the actually electrode that records the activity which controls. So with a system like that, you can do a lot. So this is a person who has a tetraplegia, so paralyzed from the neck down. And he has an implant that you just saw in his left arm. And here he is using his left arm. Specifically in this application here that we did the research in Aalborg in Denmark at university, jointly with the company Freehand in Cleveland. So what we did is there's an electrode also positioned on a digital nerve. This is a nerve which goes to the index finger, and those are the signals recorded, not to confuse you. But the person can, as you can hear, use the arm and feed himself, and that's one of the main engineers, Andreas Sinman. So they're having a social time. Martin Haugland, you can hardly see, as these two guys are the most responsible for the development of this control, closed loop control for the eating, which may prolong and provide better functioning with this. There is actually more than that, and the group that I mentioned with Gregoire Courtin, they have a plan to make it even better, but that's still a plan. So in order to do this, that it works completely at the subconscious level, one thing that can be done is there are, at this point, electrodes that can be implanted reasonably easy into the brain structure. And when these electrodes are implanted into the brain structure, they will pick up the activity. So as you hear here, there is an electrode array. This electrode array has needles that are pushed into the brain. Signals are coming to an implantable device. With this implantable device, process the signal. And when the signals are processed, and this device is used, as you will see a little later, in a device which is called cochlear prosthesis, it sends signals to the controller, which is somewhere on the belt or whatever device. It sends wireless signals to the implantable freehand system that you saw before. And when you look into the final depth, you will get an excellent function. Now, I will move now on to the second part, because the one part that we lose was the motor deficit, and the second one is the sensory deficit. Sensory deficits, the one that we see every day, is a deafness. And the deafness can be that someone is born deaf, or it's because of something else cannot hear at all. And the second one is a blindness. In people who are born deaf, you can do things and use the system that I will describe. In blind people who are born, this blindness, it's not politically correct, sorry. So in that, you can use only in humans who lost their vision. Someone who was born blind, there is no system at this point that can assist this person actually to regain. That exists is there are 12 peripheral nerves that are connected directly to the brain. And what I will be talking on two of those is one, which is going to the cochlear nerve, which is for deafness, and the second one is going to the optic nerve. Now, so what you saw here is one of the examples of how a system that is implanted, and it is implanted both binaural, both sides of a young person. And the best way to do something like that is, if someone is born deaf, to actually implant the device before this person is 2 years old, because then you can allow a normal development of all the brain structures. So what's and how engineering steps in this? That's a normal auditory system. Sound comes into the ear. This sounds generates vibration of a tympanic membrane. Tympanic membrane moves three little bones, which are called malleus, enos, and steps. And this little bone hits here, another membrane. This membrane generates a vibration of a liquid. And these vibrations of a liquid generate the hair cells move. These hair cells, when they move, when they move at the entrance into the cochlea, then someone will hear this as a high frequency. And if it generates more vibration of these hair cells deep, then we will feel that and we will sense that as a low frequency. So activating various parts along this cochlea will allow this is actually how it looks. My principle is the following: this connection is lost between what you can do is you can use a sound that's a microphone in the cochlea, and when this electrode is active, we will to 22 channels or similar. What you can do, you can easily, without major problems, generate signals that are efficient for what you actually need to do. Now, further on, that means basically in engineering terms that sound goes to a microphone, the processor, and that's the signal that will come. And that's actually the demonstration that comes directly. It can be implanted in various places. The biggest developer in Europe is in Innsbruck, and Medel System makes that. And the two other major developers are in Australia and United States. And there are thousands of individuals who have a device like that. So this is what I here for from the point is process. But the device should be implanting within the 2 years of. If you implant the device later, then the development of hearing will not be normal. And if someone cannot hear, then the development of a central nervous system, meaning the cortex, is slower. And individuals who are deaf, they don't have and cannot build the knowledge like people who can hear normal. So it is important to start very early. It is interesting, and I should mention that there is a society in the world which is called capital D, and this society of capital D actually is resisting and rejecting that. And they treat this disability as a specific culture, and they disagree that deafness is a disability. Obviously, I think that that's not really good, and I don't understand why this exists, but that's an important element because for engineers to understand that when they're building and developing things, they have to figure out what patients really want. They have also to understand what other stakeholders want, because someone has to pay for this reasonably or unreasonably expensive technology. And if there is no one who is going to pay, so the healthcare system doesn't support that, then everything is in a problematic stage. Now, this has been our implantation that I was mentioning. So the final element that I will be talking today is the restoration of vision. And with the restoration of vision, there are several approaches. One is actually to stimulate directly cortex, because the signals there. The second one are to activate the cells which are stored in the retina. And the third one is to stimulate and activate the optical nerve which connects retina and the cortex. How this all looks. So if you look into the vision system, that's an eye. And on that eye, obviously light comes in and it comes to the part which is called retina, a very complex structure which is shown here. So when the light comes, it actually activates the cells, that's here. When it activates the cell, various cells are activated, and you have cells which are for light, for and other things. And then signal, which is actually coming here, it goes to the optical nerve. Here is the blind spot and optic nerve. So the signals go to the optical nerve. When it comes to the optical nerve, it goes and comes into the region in the occipital, on the back of the head, as you can see here. And there are various regions that are actually responsible for recognition of motion, form, relays, and other color and form. So what you need, if you activate the nerve here, the retina here, then the signals will go to the system and come to the cortex. Now, when when these signals are traveling, the signals from the left eye, part of that goes to the left side of the brain, and part of that goes to the right side of the brain. And that's the way three-dimensional, because we have in both eyes, both sides, so we can actually figure out and we learn what we see. An important element is actually that we are always, and we can see only by actually comparing what we have in our visual memory already with what with the signal that is coming. So someone who does not have any experience on what an image is cannot actually see, cannot recognize, because this person doesn't have the anticipation of what is an image. This I'm saying because a person born blind, there is no way that you can do anything in actually to build up the visual system. You can provide other means of activation, but you cannot, because this person does not understand, doesn't have a perception of what is an image. In individuals who lost their vision because of various diseases or injuries, in them, what you can do is you can actually activate, and this is what I was talking at the beginning, is activating right here, and that is at the retina. Now, one possible way that I mentioned before is you activate directly the brain, or the other one is the retina that I was describing before. When you try to activate the brain, this means that you put an electrode, a cortical implant, very similar to the one that I showed you before in the research that is done in Lausanne and Geneva. And if I activate the electrodes that are here in a form, then I'm expecting the person can see here. So this is a stimulation pattern. Unfortunately, the brain is not organized like here. So the letter A that you see here, or any figure that you see here, is not represented geometrically here. So if you activate letter A like it is here on an array, you will not get the same elements. So this is just to demonstrate. If you position an electrode on the brain and here's the position of the electrode, an X-ray image of that. And you activate these peaks here, 1, 2, 3, 4. Activating point 1 will result with the activity that the user, a person who has this implant, will say, I see a little light, which is approximately 2 centimeters or so, in my field, which is at a distance of 1 meter with a diameter of 2 to 3 centimeters. If I activate afterwards, so for example, 51 and 28, so 51 is the electrode, which is right here, and 28 is the electrode, which is here. So these are not really one together, but they come by. So the organization of the cortical cells is not geometrical, and that makes it very difficult to use that. Research that was done mostly at the University of Utah and then expanded to other places, and the development of the electrode showed that it is necessary to have at least 625 microelectrodes, which at this point doesn't exist, and to have a resolution which will be at least 20 by 25 to get an image. And then you have to figure out how to activate specific cells to make a geometric form, because it is impossible to learn this new pattern. So that's the reason that the most of efforts are actually in the domain of using the retinal prosthesis. The retinal prosthesis means a camera is recording, and that signal is transferred and stimulates directly retina by electrical signals with geometrical form that you see here. So there's a set of glasses, and this set of glasses incorporate a camera and incorporate a wireless device which communicates with the implant, which is within the eye. And here you see a person, blind, walking with these glasses. And so far, and this project is mostly led at this point by the group at Keck Institutes in California. And they have major effort. That's an enormously big project which puts together many of the technical centers, including some of the military research and military results in the United States. But it turns out to be a very effective thing. So a retinal prosthesis means that's the retina, and those are the blood vessels, and that's the reason why someone becomes blind, is actually something like that. So the set of glasses with a device which comes here, with the wireless communication to an implant. This wireless communication to an implant activates the cell, which are in the retina, that's right here. And when these cells are activated in a specific form, signals travel through the optical nerve, meaning that the optical nerve needs to be intact. And when this comes to the brain, a person can see. Now, the vision at this point is still limited to black and white, no colors, and it is limited to relatively large leaves. And this is just the beginning of this lady, of the process of a lady learning how to use that. The process of learning to use a cochlear prosthesis is a process which goes somewhere between 3 weeks and 3 months. The process of learning to get an image is a process which is very fast at the beginning. You're talking about 2 or 3 sessions. But then to improve that works much more complex. At this point, there's progress, and these devices start to be applicable so the person can recognize some colors. And actually, I had a chance to see there was a person driving in a parkway in the vicinity of the rehab center. So now we have also detection of motion and other elements. So this will end my presentation here. And what I wanted to say to you is the following. The engineering, and that includes development of new materials for electrodes, development of microcomputers that can process things in real time, development processing techniques that will operate in real time, and understanding how to integrate all of this into a system that controls the biological structure to improve the quality of life. This improvement of quality of life means a lot because a person who loses motor ability comes in dystrophy, disuse atrophy, and many things because someone is paralyzed are leading to other deficiencies in the life and complicate the whole story. Thank you very much for your attention.
Thank you very much, Professor Popovic, for a very interesting lecture. Any question from the audience? Or?
Maybe about the materials they use. Professor Popovich. This is Susanna from Faculty of Science in Banja Luka. Thank you very much for a wonderful lecture. I was just wondering a little bit about the materials you use for prosthetics in order to avoid, of course, the rejection and infections, etc. Can you tell us a bit more about that? Biocompatibility of the materials you use for prosthetics.
So we're talking about biocompatibility. Obviously, things that need to be considered are, first of all, that this is safe. And speaking of some materials, titanium is obviously the metal of preference that will be used for anything. Electrodes that are used for direct contacts are either made from platinum iridium, but it can be also, you could use a stainless steel for some of those. Insulation made of Teflon, preferably, and some of the polyurethane are. So if I have to select something that will work very well, if something that is moving, then it will be stainless steel electrodes that you bring this to, or platinum iridium, which is my preference, isolated with Teflon, obviously sterilized and everything else. Problems that are typical for all the implants, the bigger the implant is, the bigger is the chance that something will go wrong. So specifically, the problem is if you have a relatively large implant. This implant, because of inertial forces, will move, and it will generate a gap within the body, and this gap will be actually a very nice nest for infection, and everything can die within a second. The problem with all of these implants is also when you have an infection, it will travel along the lead, within hours. So a small infection at the skin, which come to the nerve, if you have something in the nerve, in less than 24 hours. And when it comes to the nerve, this nerve is dead and the electrode is dead and the whole thing dies. And there are experiences in the world where that happens. Now, obviously, the technology with wireless is working very well because then I can avoid leads and wires. But the problematic issue is how to get the energy to the battery that is inside. Absorption of a tissue of the energy that you want to transfer is too large, and getting the sufficient energy to drive and control implantable devices is problematic. So maybe I answered partly to your question. So silicone works very well, obviously medical silicone, and there are new materials that are coming, and we'll see what other things will do. Obviously, you can use graphite, you can use Kevlar, you can use, but the main metal elements are still titanium and stainless steel.
Thank you very much, Professor, for your answer. Any more questions from the audience? If no, once again, thank you very much, Professor Popovich.
Thank you very much, and I'm glad that I succeeded to get us back in time at 10:30. Okay. That's the reason I was speaking a little faster. Okay. Have a nice day and good luck.
Thank you very much. I'm happy to announce our next presentation, especially because our Professor Suzana Gotović-Atlagić is here with us. Now she's come as the Bosnian and Herzegovina representative in the COST Scientific Committee. And this presentation, it is not devoted exactly for the science results. She will speak about the importance and the methodology of partner and sharing participation of the inclusive countries in COST Association supporting action.
Assistant Professor Dr. Suzana Gotovac-Atlagić graduated from the Faculty of Technology Banja Luka in 1999. Under Japanese and Swiss national scholarships, she completed her master and PhD studies in Switzerland and Japan. She spent 8 years abroad studying mostly environmental nanotechnologies based on polymer, carbon, and metallic materials. After returning home in 2007, she worked at the National Wastewater Laboratory for 8 years. From 2015, she has worked full-time at the University of Banja Luka, teaching at the Faculty of Natural Sciences and Mathematics and the Faculty of Medicine. She is working on the capacity building as the team leader of 3 projects funded by EIT Raw Materials, a coordinator of 3 national projects, and the 3.7 million euro worth impact project for the government of Sweden. At present, she is the president of the Assembly of the Association of Engineers of Technology, Republic of Srpska, and also the coordinator for academic exchange at her department. Her strong ambitions are activities on the internationalization of education in Bosnia and Herzegovina, but at the same time, she is the vivid activist against the permanent brain drain from her country. In the period between May 2040 and May 2021, she was, and she still is, the representative of Bosnia and Herzegovina in the Scientific Committee of the Cost Association in Brussels. In that period, the number of participants in the cost actions has increased fivefold, and she will today tell us more about the participation in the funding scheme. The floor is yours, Susanna, Professor.
Thank you very much for this beautiful introduction. And I'm happy to be here. As you could see, the emphasis is on my, your microphone should be off. Just a moment. Is everything okay? 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, we apologize for technical problems. Maybe this microphone is also on.
It is turned on.
Off. It has to be off. So maybe I speak too loud. It's the usual situation. Nevertheless, I thank you all for gathering here to hear my story. It will be oriented toward the people who are complete beginners into cost association, who have never participated. But in one part, I asked some of the colleagues, I know some of you in the audience are already in cost actions. So I will emphasize a little bit something new for you. So I ask you please to listen to that part of the story. COST is a wonderful association. I think it celebrates the 50 years this year, so it's their birthday this year. And it's been 6 years that I'm active in that association. I'm in conflict of interest, so I'm not in any cost action. I myself cannot participate in projects, so I'm just a representative of my country. And this is something that is part of this activity today, to present you a little bit about cost, is part of something that I'm usually doing also in Banja Luka or around Bosnia and Herzegovina, is the fact to actually promote the internalization which we can have in this country, but at the same time really to look for the opportunities to increase the employment, to increase the chances for our young scientists to do interesting research in our country, while at the same time collaborating with many people abroad. Obviously, from my biography, you see that I did spend a lot of time abroad, and it was really precious for me. It's every day in my head, in my work, all the time. I remember my supervisors, my colleagues from Japan and Switzerland, and it really did change my life. But what didn't change was my love for my own country. And I'm the happiest person because I really live here, and I'm happy to raise 3 children in this country. I would never change it. But we have to be really open, especially because of the geographical position of the Bosnia and Herzegovina as a crossroad between Europe, Asia, East, West Europe, and everything that we already know. And what is wonderful, the things that are happening that I'm really repeating to my assistants every day, is the fact that it's been 15 years that Bosnia is able to participate in most of the European funding schemes. So there is no excuse not to be funded and not to be a good scientist in this country. We do not have to rely on our national fundings, although we are happy to say that it is increasing. Our national funding is also improving, and it has to improve, that's for sure. But there is no excuse. All the European funding schemes are open, as well as the cost, which I will talk today. So all we have to do is have this basic knowledge of English, basic communication skills, and of course, a lot of imagination in our scientific areas where we work. And then everything is open. All the colleagues are open. All the emails of the scientists around Europe and around the world are visible. You can find people who do the similar things like you and make strong networks. And networks are what COST is about. So maybe switch the slide, please, a little. And just a few lines about the cost. You can, of course, read more on their homepage officially. And 50th birthday, they are funded through the Horizon 2020 scheme, which is changing from this year to Horizon Europe, obviously. And typical budget for the action in the project, of course, is around 150 euros per year for the whole action for all the participants. And then cost is really aiming at supporting the networking. So this is different. You have to keep in mind, if you are the beginner here, you have to keep in mind that you can't buy equipment, you can't buy chemicals. So cost is not financing the research per se, it's financing networking. But it's equally important as the equipment which we need, of course, in daily life. So one of the main goals of these whole networkings and thousands of meetings and seminars and schools that COST is so generously supporting is actually to build networks which will write larger proposals, innovative proposals, proposals in social sciences which will lead to important changes in societies. So most of the COST actors can be proud to say that actually they did finish after the COST action as a Horizon 2020 or some other larger projects. And of course, in the future, the goal is to have strong Horizon Europe proposals. Next slide, please. So as for the members and positions, you can also check these on the main site. What is interesting is, of course, Yugoslavia has joined the COST when it was established in the 71. And today it has 38 members, our country as well. One cooperating member, Israel, which is quite active. You can find Israeli scientists in most of the actions. And one partner member, which is South African Republic. But in the blue-greenish color on this map, you have something which is marked as inclusiveness targeted countries. Obviously, these are not only the countries which are out of EU, but also some EU countries which still lack enough support for the science. So they are much targeted with cost, and cost is really strongly promoting the necessity of their participation. So this is excellent opportunity for us, obviously, because we are desirable as such. Colleagues from the more developed countries can transfer us knowledge through this, and they get points for that. Next slide, please. Bosnia and Herzegovina position in the COST, as you see, it didn't join in 2009, but in 2009. And the first applications, of course, were submitted jointly with the colleagues already next year. The main office in the Ministry of Civil Affairs, and I really must praise our Vice Minister, Mr. Amar Mirazdija, who is a wonderful senior officer. He's really helping out to organize these promotional events, and he's strongly advocating for Bosnian participation in COST, as I do also. And he's also following all the trends in European fundings and giving us information to be able to prepare ourselves. And obviously you see the different subjects in which we already participated, but next slide, please. Okay, the increase, I think it wasn't really fivefold as it was written, but we do see a really large increase. Of course, Mr. Mirazdija and me, we did a lot of work on this direct promotion of COST on events such like this, or some school workshops around Bosnia and Herzegovina. But I think it's simply the scientific community is waking up. We are getting more involved. It's not just the promotion of COST, but in general, you do join your colleagues, you keep the communication alive, so you hear about COST from everybody else, and you start to join. Next slide, please. But what I would like us to be is simply confident in the sense that our country does have a lot of potential for wonderful networkings within the COST, and of course for future Horizon Europe proposition as well. As you know, I'm always speaking so much about natural resources because we really are this little small heart-shaped country. We just need the peace, everything else we have. So we do have wonderful natural resources. We are talking about tens of millions of tons of bauxite, iron, pyrophyllite, bentonite, kaolinite, iron, zinc, everything. So we're so rich in mineral resources. And what is interesting is that we now have so lively mining activities around, and of course processing industry. We have alumina here, we're proud of them, and so much so many things are going on around. So we do have a lot to offer to Europe in that terms, because unfortunately, most of Europe is not digging. Nobody is digging. There's a lack of processing industry. So most of the West Europe, or in general, the European Union, are quite dependent on Asian sources, mostly on China. So this is a moment of our chance really to promote, okay, we'll promote our mining, we'll promote our industry, we'll promote Bosnia and Herzegovina as a strong source of different raw materials and also the products which we have. But what we have to keep in mind is to keep it green, very green. So we have to do our best really to keep the country clean. And all these subjects, when you look at them integrally, we are talking about mining, about processing industry, environmental issues, of course, the social issues, because the stronger the industry we have, the more that we interact between Srpska and Federacija, the stronger peace we will have in this country, which is extremely important. We are raising our children here. We can't change that. So these are all beautiful subjects for future cost actions. Why not? Network with people in Europe, give their best experiences, and implement them in our country. Next slide, please. So I just made them visible in that sense. This is all I was talking about. So of course you will get the material. So list a little bit to get the ideas about what we can actually do, processing, mining, food industry, and everything that we can offer to our colleagues and make new networks. Next slide. How to efficiently join the cost. As I say, some of you are already veterans in cost, but some are really young. I see young faces here who never have joined. So I will talk about these two categories of you. Next. Two options are possible. The veterans already know that it's possible for you to somehow attach to the already ongoing project, which is quite different comparing to other funding schemes in Europe. In cost, when some colleagues, some consortium get the cost action funded, they do, of course, promote it. They get a nice website about it. The cost website is also promoting it. So if you manage to learn about that on time, when the action is really in their early phases, you can kindly ask the chair. It's not called coordinator, it's called chair. The chairperson to get you involved in that action. So this is really interesting because then they get, of course, a little additional financial support for your participation. And this is highly desirable. And as a member of scientific committee, which I usually spend 3 or 4 meetings in Brussels every year during these 6 years. So each time on these meetings, we have a lot of discussion how to increase the participation of inclusive and targeted countries like ours. So they're very much welcome. You are welcome in actions. What you, of course, have to keep in mind is that you have to keep to your subject. Of course, you are going to ask the chairman of the action, which deals with something that you already are researching. And the second option is to write your own application. And here I see the senior faces of the people who are already in cost actions. So after this beginner's phase, we should really try to write nice proposals by ourselves, or at least to get strong networks, which can be led, of course, by others, but to get involved into the writing itself. So next slide, please. This is just the short explanation about what I said about the beginner's phase. So please just read it when you get the material. You can check a little on the website of the cost, find some newer actions which are related to the subjects in which you are doing your research or industrial work, and ask kindly the chair with a nice introductory letter, some appropriate presentation about your work, and I'm sure they will positively answer to you. Next slide. But here is something that I want to talk about, this writing of proposal. Writing is really important and it's not difficult. It's not difficult. Even if you don't speak a perfect English, you can always ask for help in English. It's not such a question. Somebody can help you. I also get my proposals always checked by other people. So the cost proposals are not too long. They are somewhere between 15 to 30 pages approximately. And the most important thing at the beginning is to have a little consortium, to have an action consortium, to have few of your colleagues around Europe who will join you and who do the similar work. And as I say, since the cost actions are not funding the research and the equipment, it's best for you to already have at least some small national project, or if you are industry, to have some means for doing the physical part of the research, and then to get stronger with the financing of your networking through the cost actions. So please, I encourage you strongly, write your proposals, get your networks, learn from the colleagues, expand. Each time you participate in each cost action, in each project, in from any other funding, of course, you will get more educated, you will get more experience. Next time, every time it's easier. So you can really create a wonderful atmosphere for your colleagues at your workplace, at the faculties or factories where you work, by getting people to come to see Bosnia, to see our capacities, to expand the possibilities for our industry, to get our social work or social questions under the loop, and really improve the life, the peace, the collaboration between the people in this country through the cost networkings. Next slide, please. So I want to talk about a little prejudice for a few minutes. That is the fact that sometimes I do hear from colleagues in our country some kinds of excuses. You know, you often say, no, they don't want to finance us. I didn't get Horizon project because I'm from Bosnia. It happened to me also. I was rejected 7 or 8 times, I think, in Horizon. But I could see that my points were rising. And this is similar in cost, even it's better in cost, because in cost, you write your proposal in a very specific manner. That is, you keep the identities of the proposers completely a secret. You have to be completely anonymous when you write the proposal. If your identity can be somehow guessed or found out from the text of the proposal, you will be disqualified. So what this tells us? Cost values only excellence of the proposal. Only excellence of proposal. So your proposal has to be excellent. Your goals for education, networking, expanding of promotional events, whatever is your plan, has to be strong, nice, particular, of course. But your identity is hidden to the evaluators, because you feel in different fields. You feel the field where, of course, you put the names of your consortium, your name as a chair, and other data about the participant. But this is the administrative part of the proposal, which is not visible to evaluators. So this is a wonderful thing that really shows us that colleagues from European Union do like us, they want to support us, and this is a really fair game. So I encourage you strongly to be confident and really to try hard on that. And I'm sure that your excellence will be recognized through this excellent funding mechanism. Next. So this is the similar thing. This was just a resume of what I was telling you. So I didn't put too many data about the procedure itself, because of course it would take a long lecture, but anything that you need to ask, I'm completely open for any question. My email is visible on the internet through the official email at University of Banja Luka. So any question you have until the end of my mandate, which is in May, but even after that, I will be happy to answer. And at this moment, I just had the contacts with the Vice Minister, Mr. Meragia, to ask somebody who is going to be after me. And I'm really happy to be able soon to educate and to prepare my young colleagues, somebody who is coming after me, to prepare them to do the same thing, to encourage you every year to really be open and be international in a sense, and really work hard on our joining to the international scientific community. So you are open for any question at this moment if we do have time, and of course, as I said, by email. Thank you very much for your attention.
Thanks a lot, Susanna, for a very interesting presentation. And we have a time for the questions. Please, if you have any questions.
I'm kind of motivational speaker always, so every story finished with patriotism. Dear colleagues, you're a little tired. These are 3 lectures in a row. but we can see each other also on the coffee breaks. I will be here until tomorrow noon. So also we have a little stand with the promotional material. My young assistant Mariana is there. So please do not hesitate to take plenty of the promotional material for you or for your colleagues. And yeah, so.
We reached the end of this session. I'd like to thank once again a lot of all three lecturers. And now we have the coffee break until 11:30. Thank you.
Welcome back. Our next lecturer is Professor Uroš Cvelbar from Jožef Stefan Institute from Ljubljana, Slovenia. And his plenary lecture is on plasma as a tool for the contamination of natural toxins.
Professor Dr. Uroš Cvelbar graduated in 2000 from the School of Physics and of the Faculty of Mathematics and Physics, University of Ljubljana, Slovenia. In 2001, he became the young researcher on the MSZS grant. The Cvelbar's PhD was awarded in 2005 in the field of material science and plasma technologies by the University of Ljubljana. He is a full professor and the head of the Department of Gaseous Electronics, F6, at the Jožef Stefan Institute. As part-time, he works as a professor and teaches mostly postgraduate courses in Ljubljana, other European universities, for example, University of Barcelona, Thomas Bata University, etc., as well as outside the EU on Shanghai Jiao Tong and Mahatma Gandhi University. As a researcher, Professor Cvelbar also worked at CPAT laboratories at the University Paul Sabatier in Toulouse, France, and at the University of Louisville, USA, at the CSIRO and University of Sydney, Australia. He was and still is the chief and the co-chief investigator on many MSZS, the industry and the EU framework projects, including H2020, Future and Emerging Technologies program. He is a member of ECS, Executive Board of Division for Dielectric Science and Technology, and chair of Plasma Nanoscience Society. Dr. Cvelbar is erudite professor and in India and visiting professor at Shanghai Jiao Tong University, member of Club of Rome, Slovenian Association, and a fellow of World Academy of Arts and Sciences. Dr. Cvelbar's bibliography contains over 200 international scientific papers, 95 invited talks, 18 patents, and H-index 43. In the year 2011, he won Slovenian Puch Award along with the two other colleagues. He is the guest editor of the Journal of Physics, the ECS Transactions, Plasma Sources, Science and Technology, and associated editor of the Frontiers in Materials and Frontiers in Energy Research for Nano Energy Technology and Materials section, Microelectronic Engineering, Micro and Nano Engineering, and Nature Scientific Data. In recent years, he has been working on electrical discharges, plasma phenomena, plasma for biomedical and biotechnological applications, plasma medicine, plasma nanotechnology, nanomaterials applications for sensing, purification and energy harvesting, atmospheric plasmas and their characterization. Professor Cvelbar.
Thank you very much for kind introduction. Do you hear me?
Yes. Yes.
Okay, thank you very much. I'd like, before I start, I'd like to express my gratitude to organizer for inviting me to give this lecture, as well as to the Institute of Physics and Dr. Nevana Puvac, who's also organizer and leader of the plasma agriculture cost project, which we heard a little bit before. And I'm really sorry I could not come in person. I was actually looking forward to it, but due to institute restrictions, I'm unfortunate had to stay at home. I would prefer to stay in Koliba it's just across of you, so the lecture hall. But in this case, we had to do this remotely. So if I put it on a large screen, okay. So what I would like to talk to you today, it's about plasma as a tool for the contamination of natural toxins. So it's a topic which actually deals with, it's sustainable, deals with food. So actually covers quite a few topics which the conference is about. And I'm going to try to highlight you this new exciting technology and what the potential for this technology is. If I start with explaining what basically the natural toxins are and what the contamination is, where it's occurring is, basically all the food can be naturally contaminated. In plants, we see presence of different alkaloids, cyanogenic glycosides, lecithin, saponins. Then we have algae, which actually produce cyanotoxins, different doleic acids. And on the other side, of course, the most frequent one, which we are all familiar with, is basically bacteria, where we have different liposaccharides, endotoxins, exoproteins, etc. Maybe less familiar is fungi, of course, contamination, where the most frequent and the topic of my talk today is actually contamination with mycotoxins, or even mushroom toxins. So the question here is what the mycotoxins actually are. So the toxins are secondary metabolites produced by fungi during, when you get a fungi on any food. So when the fungi is actually consuming food and eating, it produces a secondary products which are actually mycotoxins. There's a wide variety of mycotoxins which are listed just below the table, and these are the most frequent varieties, and there's a toxicity effects which they are actually causing, and you have different types of fungi which produce this kind of toxins. Just to give you the ABC of what it means, and later on you'll follow probably some of the shortcuts, so it's easier that I explained in the beginning. The most potent mycotoxin is basically aflatoxins, which is labeled and later on labeled AF, so it's easier to understand, and it causes carcinogenicity. I think this toxin is very present in our environment as well as in Southeast Europe, including former Yugoslavia. You probably heard a couple of years ago there was a big problem with milk poisoning. So it's especially during winter months when cows eat hay, and the toxins from the hay or actually corn in poultry, they enter there basically the intestines, and they're transferred typically either in milk or directly in poultry, so in the meat. And they're extremely carcinogenic already in a very, very small quantities. So here we're talking about nanograms. And that's why this is very important, why we need to actually, let's say, limit this kind of contamination. And then the second most frequent ones, which you can find, are DON, which is also named as wormitoxins, basically because of worming and causing nausea. It belongs to the larger group of trichotoxins, which can also be differently labeled depending on the molecular structure. So it's T, HT, depending on the type of toxin. And this, as an ABC, what you'll see later on, it will be labeled like this. What is important with this toxin is that actually causes, as I said before, nausea, vomiting, liver damage, and skin inflammation. And this one is also extremely present in our daily food. So the big producer in Slovenia, we have linotes, for example. This is the most frequent toxin which they found in wheat, which comes from producers. And actually this wheat enters into the cycle, gets into the pasta, gets into the bread, and you actually consume it in a large amount. Luckily, it's not that much carcinogenic, but if it comes in a larger quantities, as I said, can cause vomiting and nausea. Then the second one also very present is FB or fuminosis. It's cytotoxic and carcinogenic, so it causes cytotoxicity. So it has more like long-lasting effect on humans. Then the next group are also ochratoxins labeled as OTA. So they cause neurotoxicity, mutagenicity, as well as carcinogenicity. So another carcinogenic factor. Then zarlenones, which actually come as labeled as ZEN. It's typical endocrine disruptor. And the last one, also very common, are ergot alkanoids, which cause neurotoxicity and endocrine disruption. So you have now this whole list of these toxins, which are actually, I mean, they're possessing some kind of threat to us through daily consumption of food. If you look on the water scale, how much of this we can find in food is actually, you have about 400 different structural types of these toxins, which causes the toxicity. The most staggering, at least for my point of view, number is that 25% of all global cereal stock is contaminated by mycotoxins. And so the 50% of human population is chronically exposed, especially to aflatoxin, which have been mentioned before. As a former Yugoslavia, we are actually very exposed to this toxin. And the result of this toxin is basically improper agriculture handling and storage practices. So if you take the food which is moistured and you put it in a silos and you store it, it's highly likely that it's going to produce fungi, and fungi results on a corn, as you see it here in the bottom, grows up the fungi, and this fungi produces, of course, toxins. And on the other side, we are actually bounded by strict legislation and regulatory guidelines. If you go back a couple of years, you might remember, I think Croatia and Bosnia, as well as Serbia, were subject, including Slovenia, were subject to the spoilage of, so they had to spill the milk away due to the contamination with aflatoxins. Unfortunately, I need to state this, I have quite a few experiences with producers. If this comes in a small quantities, the producer tend to dispose this food, or actually because you have like a point high contamination, they try to disperse this to actually meet the strict legislation. But nevertheless, we are still exposed to this. In this respect, there is actually high demand for more efficient non-thermal decontamination methods, because the thermal, these toxins are very resistant. Overall, the data which you see here, all the work, we are generally exposed to all this, depending on the area of the world. But as I said, the most common ones are DONs, aflatoxins, and ZENs. Moving further, since I work within the plasma, as well as we have a cost on plasma agriculture, the plasma, you probably very known, you know this, that actually plasma is a four-sided matter, which basically consists of dissociated molecules or excited molecules, neutral atoms, excited molecules, molecular ions, atomic ions, radicals, electrons, and protons, which do something to any surface. So in terms of applicability of plasma, we can also generate this kind of low temperature plasma in two ways. The most common ones are either low pressure systems or atmospheric pressure systems. On the top corner, this is an example of how actually you can, how you can actually have some kind of a low pressure. It's taken from Plasma Leap company, where they treat the seeds with some kind of a low pressure rotating stage. You can either generate here plasmas with different means. It's either barrier discharges, radio frequency discharges, etc. And on the other hand, what I'm going to try to talk today is low temperature plasma systems based on atmospheric pressure. So it's some kind of a cold non-equilibrium plasmas, which can be generated by either surface discharge or plasma jet. The major advantage of these systems is they're reasonably much cheaper than low pressure systems because they don't need any vacuum equipment. So what we tend to do is we try to generate plasma in ambient air and then expose those products, corn, food, to these radicals, and look at the action of the radicals to the surfaces. Here we did a lot of work with plasma jet, but I'm not going to show it. The plasma jet has some kind of limitation because it's more point of it. But so if you want to go large scale, you need to look especially at the surface discharges, which are maybe more suitable for application in industry. And you see, I showed below, it's a prototype of a system which works on a surface DBD. And, you can actually decontaminate the food running through the system, or the products which you're interested to disinfect and remove those toxic molecules from the surface. So how this chemistry works in the air surface DBD plasma is basically what we do is we have on the top a powered electrode, we have insulating material and grounded electrode below. In the first row, as you see here, you have this kind of plasma, glow at the surface of this electrode, which generates typically excited, in ambient air, excited oxygen molecules, OH molecules, hydrogen atoms, nitrogen atoms, oxygen atoms, and then in secondary. So when the plasma moves away from the surface, you get secondary products which are typically due to this diffusion and convection driven by electrohydrodynamic force away from the surface, and then you get the different so-called RMS species. So you have basically some kind of a nitrogen molecule, nitrogen oxide molecules, you have ozone, and you have other species which actually readily interact with the surface. And then there's another stage if you have any liquid interface, since, if you treat the food is typically moisture, you also need to look at the plasma liquid chemistry where secondary products are created by dissolvents species. So reactive oxygen and nitrogen species, which come from the surface. And then, of course, we need to look at all this, first the chemistries, and then we need to look at the cells and what it does to DNAs, and if these products are toxic or we decontaminated the product. So what we also need to look, actually what we look at this is the role of UV photons as well as increased temperature, because both can damage the food. But in our case, what I'm going to show you today is a case study. It's a negligible effect and doesn't really play an important role in this case. So the question here are when we have cold atmospheric pressure plasma, the question here is the interaction between the reactive oxygen and nitrogen species and mycotoxin molecules. And as well as, do we have any fungicidal activity of those species? In this way, what I'm going to show you today and what we try to do in this research is to optimize the treatment to obtain the most favorable conditions for the contamination of mycotoxin, as well as in activation of fungi. So working on both fronts, first, removing the molecules, making molecules untoxic, as well as looking at removal of fungi. So some kind of anti-fungicidal processing. What we also did, since we are scientists, we tried to describe the plasma chemistry and to highlight which species actually are the major agents playing a role in this case, as well as we try to identify the degradation products and look if they are toxic or not, as well as the mechanisms to understand better. And with this, you complete the whole cycle. And we took this technology to real case example, which I'm going to show you at the end. And it's actually the contamination of toxins and fungi on corn, and look at the effects. So the whole experimental setup and results, which I'm going to show you, are actually highlighted with this. So we use this kind of air surface DBD mesh electrode, where we expose either to mycotoxin or corn kernels. as well as fungi. We looked also in comparison to the most frequently used UVC irradiation and thermal treatment. And when we had the fungi to the so-called agent called Virkon, which is most frequently used in this kind of cases. And then we did a study on 10 or 15 toxins. I think I have here about 10 examples. And we look at the contamination efficiency using different mass spectrometry, liquid chromatography. And then we took this, as I said, to the real examples and look what is happening to the surface. And these are the pictures which I'm gonna, and the results which I'm gonna show you later on. So in the beginning, if I started with the, the gaseous plasma chemistry, we want to know what the plasma contains and what are the agents. So we look, here there's a simple example. We look at the different discharge powers, which actually yield different reactive and oxygen nitrogen species. And what you see is actually that when we use, let's say for simplification, low power, we have a low dose of reactive, so RONs, and we get very highly dominant ozone. And when we go to the high power, we get more of RONs and very few or very little ozone. So the most dominant species are typically reactive nitrogen species like NOx species. And then we compare this to the UV spectra and to see what the effect of one and the other is. What I need to highlight is also that with the operation, especially when you have the liquid, of course, the species due to interaction, they change a little bit and vary in time. When we have taken this into account too. And the second thing is we also looked at the liquid chemistry when we looked at the changes of pH, which shows a drop over a long exposure of time. And we achieved, for example, what the lowest pH is achieved at high powers. Here is one interesting thing is when you deal with the fungi typically likes very acidic environment. So in some cases, when we did a small, very short action, actually we created even more favorable environment in liquid, for example, for fungi to boost their metabolic activity. But on long run, we still show that actually we have also in liquids, as an indirect exposure, we have quite a good efficiency in the contamination. And then very frequent product here is also hydrogen peroxide, where concentration are increasing in liquids after 2 minutes of treatment. For example, if you're treating this over a constant period of time, we got nitrites as well as we got nitrites. These are most frequent cases. In some cases, the species are increasing or they're just linearly increasing up. But we also notice that there's diffusion. Diffusion into liquid is sometimes limited by low pH and a slight increase of temperature. Because if you treat something over a large period of time, then you also, because of the interaction of species, the temperature increases, but now we're talking about tens of degrees, not more. So we are still below any boiling point or whatever, what would be already thermal, so would have already thermal effect. And in this way, you have it's reasonably, a lot of people in the field are working on this to figure out this mechanism. There's a lot of mechanisms. There's 40 plus, reaction mechanisms just in the gaseous phase. Then you have another, duplication or triplication of this inside the liquid. And you see some highlights here below what is happening. So they're reasonably complex mechanisms. That's why there's so much effort is going into this. Okay, for the most simplific case, I'd like to show how actually this works against aflatoxins. So we did, this is one of the first, the most highlighted things is, the toxins are typically measured with just UV vis, and you see below this peak, which is actually significant for the aflatoxins B1. And what you see is here in this spectra is that after you treat it with UV, there's very significant, there's very little change in actually in toxin. So there's very slow interaction. So if you look at the contamination efficiency, which is on the right side, you see that actually the thermal treatment, so the classical treatment, as well as UV are pretty inefficient against the so-called the most potent aflatoxin B1 present in the milk, for example, and all the plasma treatments show very high efficiency. So it's a very high efficiency in this respect. Now you can also understand why these toxins are so much present, because they are very hard to limit or remove out of the food, the food chain through just thermal or UV treatment. And here the plasma is showing really big potential. And then we went, of course, into more detailed study, and we look at different aflatoxins and how actually this decontamination processes are changing with this. We found that, low and high pressure, high power cold atmospheric pressure plasma, the activation is very efficient. Actually, much more, since we compare it with the jets, for example, they're much more efficient compared to the jet treatment. Plasma jet treatment, and they're much more, efficient compared to the UVC treatment. Of course, you see differences in, because we have different toxins like aflatoxin B1, B2, J1, J3. They all show very quick decrease compared to the UV. You see the UV is up here in the levels, doesn't go down, but with the plasma we can just lower this in reasonably very short time. So the efficiency, as I said, is very efficient, but depends on a structure or molecule, of course. What you see by basically this different graphs, which are showing these different pathways. And that different pathways, of course, depending on a pathway and breakdown of the bonds, which is initiated by Ron species, this process is different by different toxins. Okay, going, for example, to show the second one, most frequent DONs, you see the same trend. So whatever you see here is, there are actually a couple of highlights. One is that tryptodesins are more resistant compared to aflatoxins. That's why they're also so much present inside the wheat. And the most efficient decontamination we achieve with high powers, which is highlighted by RNA, so reactive nitrogen species. And this is the most efficient decontamination for this kind of purposes. Okay, moving to the second stage, so fuminosis. Fuminosis also shows, so you see there are similarities in trends, but they vary in a little bit in efficiency. So in this case, we also achieve pretty good decontamination in a very short period of time. So we get about 90% decontamination and removal from the surface at low and high powers discharges. The most important thing is that the cap decreases the concentration of FBs under maximum levels allowed, especially for the maize products. Because this is very important, because this FBs are present in a poultry. So when you give the corn, you feed the chickens, this enters the meat, and you actually get gets into the food chain, gets eventually to humans, and we digest this. The last one, which I'm showing here, are Zarleon, where we also see very complete decontamination in reasonably very short times compared to UV, which you see it up here. So the contamination here is achieved by different. So you see, since it's a larger image, it's larger to see that when you have a low power, the contamination is a little bit slower. When you have a high power, it falls reasonably quickly, like in seconds. And so the general conclusion is to the standard method, which is UVC irradiation, which you see in all laboratories used for the contamination. This irradiation is less significantly effective for all cases of mycotoxins compared to the standard cap treatment, which we demonstrated. Okay. So you see that, I hope I convinced you that we have a method which is highly efficient against this. But what we need to look is how this actually, to understand better and how to tailor the process, to make the process run faster and be more efficient in a very short period of time, we need to identify the species which are behind this, and we need to look at the products. For this reason, we made a very large study of the degradation of that carcinogenic aflatoxin B1, where we used also high RMS, so mass spectrometry and NMR, and we look at different stages of the contamination, and we looked at the molecules which were inside. And what we found is that we come up with 4 important degradation products. These are molecules below, which I'm not going to describe in detail. But the important thing here is there is a bond, you know, so every molecule which you see below can be toxic. And typically there is a bond, single or double bond, typically with oxygen, which actually gives that toxicity to the molecule. So there's a very small variation in those molecules. So that's the important thing is. And what we looked at in this case is, can we selectively target one of these bonds to remove it quickly, and in this way render the toxicity immediately? So short exposure with species, selective species, can remove this toxicity immediately. And what we found is actually that our plasma, so the wrong species, which we are initiating from this, actually induces the breakdown of the molecules through 2 Furlan rings, which are starting at the position of CH and C9, which is basically here, if you see this. So all the breaking of the bonds occurs in this. So here the mechanisms starts. And I'm actually very proud to say that, you know, we came up with this mechanism, which is a result of actually a number of hours of work. And we found out that degradation mechanisms, maybe it doesn't mean much to you, but actually what it's important is, it's in the next slide. When we look at the toxicity of those molecules, we see that actually the toxicity drops very rapidly. So, and that's potential. So what you see here, we did the MTS and COMET tests, and what we found, you see that, you know, red zone here in the COMET test still means some toxicity for the material. But when we enter, so it's 30 seconds, and after 30 seconds, all the products which are there are untoxic. So it means the secondary products are completely untoxic. And if you look at this, so what the catch with this is, so if you look at the metabolic pathway of the aflatoxin B1, actually induces why it's so carcinogenic is basically because it induces the spontaneous reaction with DNA, which bonds here through this link. And by removing this, you saw this, actually, I told you, on the Furlan ring, we started initiate the breaking or scissoring of this molecule. So we break the bond exactly on this point. And this actually gives very quick efficiency in loss of either cytotoxicity. So we actually, we lose the cytotoxicity of the molecules, as well as we lose, the decreased strength of DNA breaks very rapidly. So even within the 60 seconds of treatment, it leads to complete degradation of these products. And we have no, if you look at the analysis, we have no significant breaks of DNA bonds. And that's another very, very important thing which comes from this. Of course, from the practical aspect, we need to look at the contamination of aflatoxin on corn kernels. So real example, when we have toxins on corn kernel, which are exposed to the plasma. So if you wanted to treat it, you want to treat this in a real case. We look at this, and you see here there's a concentration, how concentration drops. Of course, this is experimental data with a significant amount of toxins deposited on the surface of corn kernels. In reality, so here what you see is micrograms per milliliter. In reality, we are dealing with nanograms. So there, the concentration for non-laboratory practices are much lower. So also the processing of the contamination is much faster compared to this micrograms. In micrograms, I'm almost certain everyone would get cancer already being exposed to this. And what we found is that, we look at the certain properties of corn, we look at the chemical structure, and we looked at very simple method, which is, water contact angle, which is shown in the first picture. And we see that there is actually no significant change in the contact angle of corn kernels being treated. And we have very small modification in rise of oxygen concentration with a very modest increase in different oxygen bonds. So this is some kind of surface functionalization. We call this in practice. So surface functionalization with oxygen groups. And we looked at also at the ER spectrum. So with FDR, we looked at the corn kernels, and there's basically no change in the corn kernel structure. This is highly important, because then we don't have to go in the second stage and look at the organoleptic properties. So, any treatment of food leads also to degradation of organoleptic properties. And if we see that we have all, aldehyde, alkanes, ester groups, acryls, and ester groups on the surface, and they're the same or practically the same, then we don't have to go into the second stage and look into the modification of food. And this is the case in our case. The third important thing is you also need to look at morphology. This is another example. And here we have the corn kernel after treatment with scanning electron microscopy and atomic force microscopy. And what you see is also no difference in morphology between so non-treated and our treated examples during the removal of molecules. And we have no significant difference in the size or shape of the granulus. So this is much smaller part of which you don't see under SEM images. So there's basically that these granulus and shapes are still the same. And this is highly important. Okay, the last thing which I want to also to discuss today with you is the inactivation of so the fungi, flowers, and here is direct exposure. So what we looked also is not only to the toxins, but can we have some kind of antifungal effects on the surface? And what we found is significant log reduction after exposure, which induced the complete inactivation. And we compared, of course, this to the, as you see here, low power and control, and you see high power, and you see the Virkon, as I said before. Virkon is a classical chemical which is used for removal of fungi. And what you see is that actually this high power example, for example, induces notable morphological changes to the fungi spores on the surface, which is a very good sign, which also shows that actually when you look at the degradation, it shows significant degradation, so we can remove the fungi at the same time. There's a second approach which can be used in this case, so I'm not going to go much into the detail, but it's when you expose also the liquid. So if you have them in the liquid, so you have some interface in between, it shows lower log reduction, but there is it influences the metabolic efficiency. So it doesn't fall so quickly, but the metabolic, so you disturb the metabolic. So if the spores are in the liquid, you disturb their metabolic process. And in long terms, it leads to their deactivation. And that's important key message to this. So with this, I would like to conclude and leave 5 minutes for question if somebody has a question. So basically, I hope you'll take a home message that the CAP completely remove the mycotoxins. I mean, it's technology, future technology, which is rising and will rise probably as an alternative to the most classical methods. As I have shown, it removes the mycotoxins and basically leaves the food untouched. And, it works biocidically. And the most important species are those reactive oxygen nitrogen species. And looking at the price of these devices, this should, we should see this in the next decade that, a lot of these processes will be highlighted by this. And as I said, this can be, the potential of the method can be only shown if you show also the loss of the toxicity, which we have been showing, and that actually that you don't affect the organoleptic properties or properties of the corn kernels. Since, there's quite a lot of results here, I would need to acknowledge here quite a few people which also contribute to this work, but they're not authors. So Professor Križaj and Dušan Žigon from Jože Stefan Institute, Metka Filipić and Bojana Žigura from National Institute of Biology, We have strong collaboration with also partner with James Walsh, who is also designing such systems. Uroš Javornik and Janis Plavec responsible for a lot of NMR analysis. Gabriela Taučar, Kelher, and Breda Jakovic-Strain from University of Ljubljana, actually veterinary clinic, which is standardizing and the responsible reference laboratory for the mycotoxin evaluation in the food in the Republic of Slovenia, as well as Professor Gregor Serša and Špela Kos from Institute of Oncology in Ljubljana, dealing with carcinogenic effects of this, as well as to the founding agency of Slovenian Research Agency, as well as COST with Plagri plasma on agriculture. Thank you very much, and if you have any questions.
Thank you, Professor Cvelbar. Thank you for sharing your present and recent research with us. This was a very interesting lecture. Are there any questions? Questions, please. No. Thank you again.
Thank you. And I hope you will enjoy the Congress. I envy you all being sitting there, the Jahorina. I looked at the weather forecast and it showed it's snowing today. And will be snowing for next two more days.
We hope that next time we could join us here on Mountain Jahorina. Thank you again. If no questions, okay. Thank you, Professor Cvelbar. We can go with the next lecture. Our next lecturer is Dr. Nikša Krstulović from Institute of Physics from Zagreb. His lecture is on photocatalytic activity of laser synthesized titan dioxide and zinc oxide nanoparticles.
Dr. Nikša Krstulović received his PhD degree in physics in 2010 at the University of Zagreb, Croatia. He is employed at the Institute of Physics, Zagreb, Croatia, as a senior research assistant. He is the leader of the plasma unit group of the Center of Advanced Laser Techniques at Institute of Physics. He spent 2 years on a postdoc position at the University College Dublin under Marie Curie Fellowship, working on the development of laser plasma EUV light sources. His research interests include laser-produced and non-equilibrium plasmas, atmospheric plasmas, plasma diagnostics, extreme light sources, synthesis, and applications of nanoparticles by laser ablation in liquids, photocatalysis, and pulsed laser deposition of thin films for photovoltaics and sensor development. Dr. Krstulović.
Thank you very much for nice introduction. Hello, everybody. Unfortunately, I'm not there in person. I'm participating online, but hopefully next time I will be there in person. So I'm coming from Institute of Physics from Zagreb, and I will talk about photocatalysis performed by laser synthesized colloidal solutions of titanium dioxide and zinc oxide nanoparticles. In our laboratory, we are using several kinds of plasmas. So laser produced plasmas in vacuum, gases, and liquids for different applications than radio frequency and actively coupled plasmas, atmospheric pressure plasma jets, very similar to those shown in previous talk given by Uroš, and then low pressure plasma jet. But today we'll be focused on laser produced plasmas, but in liquids for production of colloidal solutions of nanoparticles. This is brief outline. I'll first show what is laser synthesis of nanoparticles in liquids, And then I will show some examples of photocatalysis of zinc oxide and titanium dioxide nanoparticles, our recent results. And I will also give some future scopes, actually our future idea how to improve the photocatalysis, and I will also mention some other applications. So laser synthesis of nanoparticles is based on laser ablation of metallic target immersed in water. This is actually known as green synthesis technique because only high purity target, high purity water and photons from the laser is actually involved in the synthesis. So unlike chemical synthesis, there are no byproducts, there are no some chemicals in reactions. So our nanoparticles are pretty much very pure, and water does not change its properties significantly. By using laser synthesis of nanoparticles, we can ablate almost every target which is metallic or semiconductor. So there is a wide variety of targets that we can use for synthesis of wide variety of nanoparticles. And such colloidal solutions are not inhalable, and we can also use laser pulses to additionally change the parameters of nanoparticles, so we can play with the size distribution, fragmentation, some reshaping, and so on. And such nanoparticles are usually very stable due to high Z potential, that there is no need for addition of additional chemicals to prevent agglomeration. And by the fact that this is a green synthesis technique, and we can say that laser synthesis of nanoparticles is alternative and competitive technique to all chemical methods used for synthesis of nanoparticles, with the advantage of synthesis of really broad or wide variety of different nanoparticles. So when the laser pulse shot the target immersed in water, laser ablation actually starts to occur, which is related to fast vaporization and atomization of the target. During the course of the laser pulse, plasma is formed. Plasma is then full of atoms, ions, molecules, and small clusters. And due to plasma expansion and plasma quenching, nanoparticles are forming due to condensation and agglomeration of all those species present in the plasma. We can divide formation of nanoparticles in liquid in two phases. One is rapid aggregation during the course of the laser pulse, and then slow growth of nanoparticles due to diffusion of surrounding nanoparticles, which is on, let's say, micro or millisecond scale. For this synthesis, we are using nanosecond laser pulses with, let's say, 100 millijoule of output, infrared or green wavelength. And you can see here, we can easily then produce different kinds of nanoparticles, for example, gold, silver, copper, and zinc oxide. And in the end, our nanoparticles have log normal size distribution. That shape due to growth of nanoparticles induced by diffusion, which is a long process. So big nanoparticles can be also formed, but in some low frequency. So water pollution is one of the greatest ecological problems today, which is expected to become even larger in the near future due to large amount of industrial waste material released into the natural waters. Photodegradation of pollutants into simpler and non-toxic components using photocatalytic materials is very promising and widely researched technique for wastewater treatment. That's why we are developing titanium dioxide and zinc oxide solutions for treatment of water, because they are most promising, most examined photocatalytic semiconductor materials due to their low cost, but what is important, high photocatalytic efficiency and non-toxicity. And now we will see how our nanoparticles actually degrade dyes in water. This schematics of production of zinc oxide nanoparticles. After the laser ablation of target immersed in water ends, on the target we have crater. By measuring volume of that crater, we can calculate actually mass of ablated material. And if we know mass of ablated material, then we know the mass of nanoparticles involved in our colloidal solution. So that what means that we can do quantification here, and that we know exactly how much material we are using for photocatalysis. In this case, we have concentration of ablated material, so zinc oxide, 20.6 milligram per liter. Then we diluted to study effect of different concentrations on photocatalysis performance. These are now zinc oxide nanoparticles. You can see that they are spherical, like small balls, but there are also other materials which didn't crystallize in form of nanoparticles, but it still contributes to the to the photocatalysis. So we cannot easily calculate a number concentration of nanoparticles, but then we are dealing with mass concentration, including nanoparticles and irregularly crystallized structures. If we separate nanoparticles, then we can see size distribution, and we have nanoparticles of the diameter of around 50 nanometers. And as I said, we have log normal size distribution here. Those nanoparticles of zinc oxide are crystalline, confirmed by the XRD measurement, typical hexagonal wood-stit structure. And due to presence of all peaks, we can say that they are randomly oriented crystallites. From UVVs, we can calculate band gap. It's typical band gap for zinc oxide. And from XPS spectra, we see that there is a band correspond to zinc state in the lattice and oxygen state in the zinc oxide lattice, but there is also some vacancies and OH and CO groups which are related to chemia-absorbed contamination. To prepare nanoparticles, we are dropping on the silicon substrate and exposing to air, and that's the reason why we in XPS spectra also measuring some contamination, but that is not coming from water, that is coming just from the fact that we expose our samples to the air. For photocatalysis, we are using UV lamp with power irradiation in UVA, UVB, and UVC, as is shown here. And if you follow that green line, you can see that our zinc oxide nanoparticles, that's photoabsorbance of zinc oxide nanoparticles, have very strong absorption in UV region. And in visible, there is almost no photoabsorption. That's why zinc oxide can be also used for very efficient, for example, UV coating material. And you can see also here spectrum of methylene blue and rhodamine B, which do not interfere with zinc oxide nanoparticles. Here we exposed methylene blue, rhodamine B. We mix it with zinc oxide colloidal solution and exposed to UV radiation. You can see here that spectra of methylene blue and rhodamine B decreasing in time of irradiation. And by plotting intensity versus time, we can calculate degradation rate for each case, depending on the initial concentration of zinc oxide nanoparticles. And we see that the higher the concentration of nanoparticles, of course, the higher is the photocatalytic activity. And in time, you can see that our initial solution, which is very dense in the beginning, becoming more and more transparent due to degradation of dyes via photocatalysis. Here we have how degradation rates depend on zinc oxide concentration, but also on the initial relative concentration of the dye. And from this table, we can see that half-time, photodegradation half-time derived from these images is showing that for initial relative concentration of dye of 0.5, we need only 7 minutes to degrade half of such dye intensity. For methylene blue and for rhodamine, we need only 13 minutes, which is, let's say, pretty fast photodegradation rate. Of course, the higher the concentration of zinc oxide nanoparticles, the higher is degradation rate, but also as initial relative concentration of dye is the lowest, then also photodegradation rate is the highest. Our titanium dioxide nanoparticles, we also can easily synthesize by shooting on pure titanium immersed in water. We also get nanoparticles with a little bit of irregularly crystallized material, but our nanoparticles after ablation, so as prepared, are not crystalline, as you can see from side images. But after heating for 6 hours and 90 degrees, our nanoparticles become crystalline. And size distribution of as prepared nanoparticles is here. So peaking at, let's say, 8 to 9 nanometers. After heating, the size distribution is more narrow, peaking at 5 nanometers of average size or diameter of nanoparticles. And that nanoparticles then we can use because they're crystalline for photocatalysis. So after heating at 90 degrees, our nanoparticles become crystalline. This is confirmed by XRD analysis, but that crystallinity actually comprises of mixture of phases of rutyl, anatase, and McNally phases, as we can see here. And from our XPS spectrum, we can recognize that around 9% is related to titanium 3+ ions in the lattice, which are responsible for increased catalytic activity, so increased in UV region, and also they allowed for photocatalytic activity using just visible irradiation. From UV spectrum, we can also calculate band gaps. From that analysis, without going into some details, we can say that dominant is actually anatase phase, but with the presence of rutyl, with a little bit of rutyl. So we can use our system for direct comparison with iron oxide P25, which is commonly used powder for photocatalysis, because that powder is also optimal mixture of rutyl and anatase phases. And again, if we calculate crater and mass of ablated material, we can deal with the quantification, so we know exactly how much material we are using for photocatalysis. And then we compared photocatalysis performance with the same amount of iron oxide P25 powder, just to compare is our system better or not with the commonly used commercially available powder. As you can see here, methylene blue is degrading pretty much fast using titanium dioxide photocatalysis. it becomes more and more transparent in time, and after, let's say, 60 minutes, it's almost completely transparent due to complete degradation of methylene blue in the liquid. You can see here how relative intensity depends for methylene blue in time using UV and visible light. Of course, performance is better for UV light, but there is also a certain amount of degradation of methylene blue using only visible, so solar irradiation, which is pretty much interesting. And that first graph actually shows that our system is showing photocatalytic activity in visible region, and that is in both cases, so in visible and in UV, better than the same amount of P25. We also perform photocatalysis of diazepam measured by HPLC, which is a drug widely used and widely spread in the environment, of course, and it's not for many decades due to its photocatalysis, and it is highly susceptible towards OH radicals and UV radiation. So we also perform photocatalysis using titanium dioxide, and we show that there is some photocatalysis invisible, again, probably due to presence titanium 3+ ions in the titanium dioxide lattice. And there is very fast degradation in UV, where P25 is a little bit showing a little bit faster photodegradation than titanium dioxide nanoparticles. And to summarize, we can calculate degradation rates. So for methylene blue in UV, titanium dioxide showed 50% better performance than P25 powder. Invisible for methylene blue, there is 4 times better result than the same amount on P25 powder, and it works invisible, what is also a result. In UV, P25 is 2.5 better than titanium dioxide, but invisible again, performance of photocatalysis using titanium dioxide nanoparticles is, let's say, 2 times better than commercially available powder. All those results actually promote us to research such nanoparticles and to think how to even more improve the photocatalytic activity using some additional techniques to, let's say, mixture that nanoparticles with other metals or semiconductor material of interest. And in the near future, so we want to reach the enhanced UV photocatalytic activity using metal oxide nanoparticles, let's say by doping of such nanoparticles with noble metals. And also we want to reach the photocatalytic activity in visible, so using only visible or solar irradiation. So we will focus on production or synthesis of 2-component nanoparticles. So we plan to mix metal oxides with metals or metal oxides with metal oxides just to get just to dope that nanoparticles with other ones to get enhanced photocatalysis. We also want to use that nanoparticles due to their wide variety of applications and very nice performances, very nice for example, for incorporation in textiles, either by atmospheric pressure plasma jets or by extruder, to get better UV protection coatings, where zinc oxide nanoparticles are very interesting, to get antimicrobial activity. Again, zinc oxide, titanium dioxide, silver nanoparticles are of interest, and also to get biodegradation of such textiles. And in the end, we want to also design nanoparticles for incorporation into food packaging polymers using atmospheric pressure plasma jets to get better barrier properties, to get also antimicrobial properties, and also to test the leaching of the nanoparticles from the polymer into the food when they are in contact with the food. These are my sponsors and our project called Laser Synthesis of Nanoparticles and Applications. These are my colleagues from different institutions. I want to point out just that we get very nice infrastructure project, and we are building a Center for Advanced Laser Techniques here at the Institute of Physics. And I think within six months it will be open. And thank you for your attention.
Thank you, Dr. Krstulovic. Are there any questions?
I think I just finished just in time.
We have time for one or two questions before because we are before coffee break.
Okay, thank you, Dr. Krstulovic, for a nice presentation. I'm Dragana Gajic from Faculty of Natural Sciences in Banja Luka. We're basically doing the same topic. We are just using some different synthesized methods as mechanochemical methods for synthesis. I just want to ask you, did you try to use these materials, zinc oxide and titanium dioxide, for photocatalysis experiment under the sun exposure? Because we don't have UV lamps. We think that we get some great results, but with a greater time. So did you try, or you're just waiting to do some other synthesis to do these experiments?
Yeah, I'm just waiting to buy a device to mimic the solar irradiation.
You don't just do it.
I will buy a lamp.
Okay.
Solar irradiation. So far we are using UV, and we cover UV with glass to get just visible irradiation from HG lamp.
Yeah, and just one more question. Which methods do you use? Because you have colored solutions
Yes.
Which method do you use for separation these dyes solutions from colored solutions when you determine in time concentrations of your dyes?
UVVs in time.
Yes, but which method you use to separate those nanoparticles from solutions which you determine with US?
There is no need to separate nanoparticles from dyes, because they do not interfere in spectrum. As you can see here, this is zinc oxide curve. This is rhodamine and methylene, rhodamine B and methylene blue. So they do not interfere. So we are measuring full spectrum every 10 and 15 minutes.
Okay, thank you very much.
Yeah, thanks.
Any question? More question?
Hello, thank you very much for a great presentation. Dineksha, I would like to ask you, I'm Susanna from Banja Luka again. So I would like to ask you about the shapes of the particles. You have shown us at the beginning that you first get some mixture of the round shaped particles and the little sheets, or how did you call them?
Yeah, okay. So we have mixture of irregularly.
And then you showed us that
material, which is here, and regularly formed nanoparticles, which example is here.
I would like to ask you about the nanosheets.
Sorry?
I would like to ask you about the nanosheets, about the sheet as a shape. I did my PhD with Professor Kaneko in Japan, and he was promoting very much these sheets shape, which are like, you know, squeezed. They called it dahlia-shaped sheets, you know. They're not so regular, not so flat, but zgužvane a little, you know.
So depending on the parameters,
the shapes, are they effective? Could they be maybe even more catalytically efficient, or
probably due to maybe increased surface, active surface, but depending on the laser parameters and the other experimental parameters, we can also get zinc oxide nanosheets.
Yeah.
That's what we get before. So the nanoparticles were not like little balls, they are like little discs, 30 nanometers thick and 500 nanometers in diameter. So they're more like sheets than the nanoparticles.
Okay. Very nice. I'm really curious about this area. We'll keep in touch. Thank you.
Great, yeah.
More question? No? Thank you, Dr. Krstulovic.
Thank you all and have a nice day.
Have a nice day too. Now we have a coffee break until 12:55 and one more lecture, plenary lecture in this today morning section. See you late. Okay. Mhm. Can we start? Okay. Our next plenary lecturer is Konstantinos Georgiou, professor from Agriculture University of Athens, chemistry from Greece, and his plenary lecture is on elemental metabolomics.
Konstantinos Georgiou, professor in the Agricultural University of Athens, is developing methods to determine geographic, genetic, or processing origin of samples, inventing an interesting new subfield of metabolomics named elemental metabolomics. Professor Georgiou.
Thank you for the nice introduction, and thank you for the nice organization. I have to confess that it was a dream of me when I was a student to come to visit Bosnia, to visit Sarajevo more specifically, because of the music played there. I was not able to fulfill this dream when I was a student, but today it's a day where I can visit, at least remotely. I hope in the near future I will have the opportunity to visit you in person. And also I would like to tell you that I have another affiliation. I'm a professor also in TMF faculty for the last 5 years. For more than 20 years, I have been collaborating with Professor Branko Bugarski there. And we have met with Branko in Saloon, in Thessaloniki. It was 20 years ago. And from that time on, I'm collaborating with him, and his students are coming to visit me, and they get some training with us. The last idea we have is elemental metabolomics. And we have trained many Serbian students from the TMF faculty. Some of them were quite capable and have developed nice careers, international careers, and got out of the Balkans, actually. Let me try to share my screen. So give me just a moment.
Professor, we can't hear you right now.
Yes, I'm not talking right now, actually.
Okay.
Thank you anyway. Well, I will talk about elemental metabolomics. Elemental metabolomics is a new subfield of metabolomics that we have defined during the last 3 years. And I'm going to give you an idea of what is elemental metabolomics, what is the importance of elemental metabolomics, and what is and how we do it. And we are going to talk about metabolomics. We are going to talk about instrumentation, and we are also going to talk about numbers, and we are going to talk about what is new. And we will talk about elemental matrices, and we will talk about what we are measuring actually, and we will talk about informatics and statistics. And also we are going to talk about applications. What are elemental metabolomics? Metabolomics is the endpoint of the omics cascade. Genomics, then it was transcriptomics, then proteomics, and then metabolomics. First, we were interested, that was 40 years ago, in DNA. Then we went to RNA, and then we were working with proteins. And now we are working with metabolites. And this is a graph that shows the importance and the applications of metabolomics. Most important is health and disease. Most of the work is about health and disease. And then it has to do with nutrition and lifestyle. These are the main things about metabolomics, the main applications of metabolomics. Let's see what are the metabolites and how many are they. We see that there are 3,000 to 6,000 metabolites of interest. Of course, the Human Metabolome Database has more than 42,000 metabolites, while more than 200,000 metabolites are present in the plant kingdom. An important project is the Human Metabolome Project that started 15 years ago. And this Human Metabolome Project was about 2,500 metabolites, 1,200 drugs, and 3,500 food components. And that was the Human Metabolome Project. And to have metabolome project, we have to have high throughput metabolomics. What does that mean? That means that we have to have the capability to analyze 300 to 800 metabolites in a sample per minute. That means big analytical power. That means that we need to have special analytical methods to realize metabolomic studies, because we have to analyze many samples and we have to measure many substances. What about elements? Elements are not studied as basic group of metabolites. Is it because it's too simple or because it's too difficult? Elements hold a huge body of information, and this has to do with toxicity, nutritional deficiencies, medicines, diagnostic targets, occupational medicine, and many others. Let's see the composition of the human body. This is a model composition of a person that is 70 kilograms, and out of his body, 96% is made from mega elements. What are the mega elements? It's carbon, hydrogen, nitrogen, and oxygen. These are the mega elements, the elements that comprise the human body. Then there are some essential macro elements. These essential macro elements are calcium, chlorine, potassium, magnesium, kalium, phosphorus, and these are making 3% of the total weight of the human body. And then there are some small percentages of essential microelements, some other modulating microelements, and some other elements, and some other toxic elements. Let's go through the whole idea. The whole idea is that 90% of the human body is with mega elements, and macro elements is another 3.25%. And the remaining are trace elements, and we are accustomed with trace elements. We are not accustomed with ultra trace elements. What are the ultra trace elements? The ultra trace elements are the elements that are lower in the concentration than the trace elements, and these ultra trace elements are around 41 elements. And if you sum all of them, the human body has just 1 milligram of these 41 ultra trace elements. It is quite difficult to determine these ultra trace elements because they have various problems. One of the problems is that they are in extremely small concentrations, and therefore we need to have special analytical techniques to do this analysis. Let's have a look at the periodic table. This periodic table is from a publication which defined this field of elemental metabolomics. And there we have a rather arbitrary characterization of elements to various groups. One of the groups is essential, and another group is beneficial. And there are some groups that are toxic, and some groups that we define them as others, and some groups are not measured. This characterization is rather arbitrary because it's not clear that some elements are toxic. Some elements can be beneficial if they are in a small quantity, but at the same time, they can be also toxic if they exceed a certain quantity. And some elements are beneficial if they are in a certain form in the human body, and they are extremely toxic if they are in a different form. So let's see the element concentrations in the human body and the Earth. We see that certain elements are quite different in concentration in the human body and the Earth. And these elemental concentrations show some common elemental nutritional deficiencies in the world. These are the basic elemental deficiencies in the world, starting from iodine, going to iron, then to zinc, to calcium, to selenium, to cobalt, and fluoride. And what is new in elemental metabolomics? Historically, only a few elements were screened. And there are some examples for studies in diabetes in blood. Diabetes is an illness that affects many people in the world. So diabetes is quite well studied. We have seen studies starting from 15 years ago, and these studies were not complete studies. These studies were assessing just a small part of the 70 or 90 elements that are around and are absorbed by the human body. And this is the new thing in elemental metabolomics. Elemental metabolomics preaches that it's beneficial to measure all possible elements in the human body. Second important and new thing is that we have developed methods to control contamination. This contamination, the control of this contamination is being done in two ways. One is in the laboratory. We use clean laboratory practices, and that is because ultra trace elements are commonly contaminated. And we use some standards from clinical laboratories and the medicine field. Beyond that, beyond the control of contamination in the laboratory, we use statistical quality control. We use some matches with references intervals, and we identified patterns of contamination. You will see further on in my presentation how we are doing that, and you will see some interesting and strange results from some experiments we had with rabbits. And these rabbits were found to have high concentrations of molybdenum. And we finally came to a conclusion after a statistical quality control that this was an artifact. This was because we were using some scissors, chirurgical scissors, to cut the samples, and we were contaminating the samples. And that was an example on how we have to control contamination in elemental metabolomics. A new thing is that we think that we have to develop databases and we have to do data analytics. What do? We have to create elemental signatures with detailed annotations, and we have to report with standards and minimum information in that. And we have to develop algorithms for data cleaning, algorithms for normalization, algorithms for signatures and fingerprints, and specialized distance algorithms. We have also to develop clustering and classification algorithms, and we have to do some network analysis. All these things could be gathered under the general term that is called bioinformatics. In the past, as we come from the analytical chemistry field, all these things were characterized some like chemometrics, but the correct way to describe this thing is bioinformatics. Let's see a bit the terminology we use. And let's define what is elemental metabolomics. Elemental metabolomics is quantification and characterization of the total concentration of chemical elements in biological samples that are and then monitoring of their changes for the characterization of metabolic processes. Elemental profiling has to do with the quantification of elemental content in a given sample of specimen. And the elemental fingerprint is the classification of biological samples using their elemental profiles. The same goes with elemental signatures. Let's talk about some examples from our work. This work was funded by various agencies, European Union or Greek agencies or companies. This has to do with a study we have done, and this study was about the status, the elemental concentration of the human population. That was a big study we have done some years ago, and we were taking 852 blood samples, and we were measuring 16 trace elements, 16 rare earth elements, and 2 actinides. That is 34 elements. That was the very first time we developed the idea of elemental metabolomics. Till that time, everyone was measuring a very few number of elements in the blood samples. At that time, we were the very first in the world that we discovered that rare earth elements could have an important role in biochemistry and in other various fields. The question here in the study was to find reference intervals for rare earth elements for the Greek adult population. That was the goal of the study. And this was a big study that had various problems of contamination mostly. And this contamination was, we have done the decontamination mostly with statistical techniques. Another project that we have done with elemental metabolomics had to do with the distinguishing of the wild rabbits from commercially grown rabbits using elemental signatures. This project has to do with Limnos Island. Limnos Island is an Aegean Sea island that has the following problem. Rabbits are growing wild and they destroy the plants of the farmers. So rabbits are enemies. And if you kill a rabbit, you get 4 euros reward. We were there and we were not killing the rabbits. We were trying to find a solution that could bring economic value to the farmers there. And we were able to distinguish wild rabbits from the commercially grown rabbits using elemental signatures. And that was important because we have found that these wild rabbits had the same elemental signatures with the rabbits in the Northern Europe in different countries, like Sweden. And another project that we have done had to do with a Greek traditional cheese. That cheese is Graviera cheese. Gravieras are cheeses that are around in many countries, and we would like to determine the geographic origin and also the milk type. This cheese is prepared from different milk types, and each one of them has a different cost. So it is important concerning food authentication to know 2 things: geographic origin, if it is Greek or it comes from another country, and second, what is the milk type that we use to prepare this cheese. For this, we have used linear discriminant analysis, and this analysis was successful for almost all cases, while some other ways of achieving the goal was not so successful. This is the very first study in the world that pointed out 61 elements in dairy products, including all 16 rare earth elements and all 7 precious metals. We have theorized and we have defined that precious metals are important authenticity indicators in food products, because no one is going to change the content of food products in precious metals because it's extremely expensive. To do this analysis, we used 105 samples from 9 different geographic regions produced from sheep, goat, and corn milk and their mixtures. And this is the map of the samples. This is a map of Greece, and these are the points where we went and we were doing sampling. I have to make it clear that a big portion of the money we spent has to do with sampling. Of course, we are a reference laboratory for elemental analysis, so many people are bringing their samples, authentic samples, and they don't charge us, and we are providing them analysis for the samples, and at the same time we get authentic food product samples. And this is extremely important in elemental metabolomics. Sampling costs too much, and you have to be sure that your samples are as described. Another project that we have done throughout the last 7 years had to do with eggs. And the question was, can we distinguish conventionally, organically, and free-range produced eggs? 3 different kinds of eggs. 3 different kinds of eggs that have different prices and 3 different appreciations of the consumers. That was the first part of the project. Second part of the project was to see if we can modulate the elemental content of the eggs by changing the feeding of the chicken. We were adding flavonoids, and flavonoids are known that bind elements, and we were trying to see if we could create tailor-made eggs that are enriched in specific elements, eggs that could be aimed to specific people that have specific health conditions. And this is quite important. For this study, we used a lower number of samples. We used 30 samples, and we used 17 trace elements, and we used 6 descriptors. And these are the results. We have seen that it's quite easy to discriminate the 3 different kinds of eggs with some simple analysis by plotting zinc and selenium. If we plot zinc and selenium concentrations, these 3 different kinds of eggs are gathering together in specific points of the graph. And that was something that we have also seen with arsenic and selenium. And that was interesting because with elemental metabolomics, we were able to discriminate expensive eggs from low-cost eggs. Let's go through again and see again and talk again about what is elemental metabolomics. Elemental metabolomics is 3 things. First thing is comprehensive elemental profiling. We analyze as many elements as possible, if possible more than 70 elements. We have to use fast analytical methods. We have to use high throughput methods. And this we were able to achieve with plasma techniques. Plasma techniques that are used for analysis. And with plasma techniques, we were able to do 70,000 measurements per day with low cost, beyond the cost of the instrumentation we have purchased. The second thing that is important in elemental metabolomics is that we have to create databases with elemental signatures. These elemental signatures are specific for specific products and also for specific conditions of the product. And this costs much. It's expensive to create elemental signatures and databases, but it is important. This way, we will be able to know what is the elemental content of a nice person before even we can define what is a nice person. And this is also important. The third thing in elemental metabolomics is bioinformatics, as I already told you. And bioinformatics has to do with algorithms and tools for big data. I take a time here to remind you that big data are the data that is used by Google to find the best way for you to travel from your home to your work, the best way to travel from Yahorina to Belgrade. And this is the same idea, the same algorithms and the same tools we use for elemental metabolomics. That is why we are collaborating with people that are bioinformaticians, and some of them are working with Google in USA. And also it's important to present our results not as concentrations, but as relative concentrations. So scaling to some reference materials is extremely important. So Another thing that is important for elemental metabolomics is reference materials. And there is a big lack of reference materials in Europe and the world. And there are many ways to fund the creation of reference materials, and it's not so difficult to obtain funds for the creation of reference materials, because reference materials are extremely important, not only for elemental metabolomics, but for all the analytical techniques that we are using. Let's have a look at how the elemental analysis was done in the past. In the past, they used some techniques that were not so efficient. We used atomic absorption, either flame atomic absorption or graphite furnace atomic absorption spectroscopy. With these techniques, we were able to do 400 to 800 measurements per day. That is not so big if you aim to do metabolomic studies. At that time, in the past, we were using also inductively coupled plasma optical emission spectroscopy. And this technique was quite high throughput technique, but it was lacking sensitivity. So with this ICP OS, we were not able to analyze small concentrations. We were not able to determine ultra trace elements. And that is the new thing on elemental metabolomics. We are aiming to determine ultra trace elements. And ultra trace elements are some rare earth elements, some precious metals, and some other elements. And this is the target point, the main target point of elemental metabolomics, ultra trace elements. This is how we are doing elemental profiling now. We are doing elemental profiling with inductively coupled plasma mass spectrometry. And this, at this point, I would like to take some time to point out that mass spectrometry is extremely important in metabolomic studies, either organic metabolomes or elemental metabolomes. So mass spectrometry is the key to metabolomic studies. It's the same for organic compounds and the same for inorganic compounds. ICP-MS is the technique of choice now for elemental profiling. With this technique, we can determine 70 elements, and we can do up to 17,000 measurements per day. This is quite high throughput. In the near future, we think that laser ablation and high-resolution ICP-MS have a big contribution. Laser ablation will be able to avoid the preconditioning of the samples, that is sampleization, and laser ablation is able to do spatial analysis because samples are not always homogeneous. And this laser ablation technique is a step to the future also, according to our opinion. Another important technique in the near future is the high-resolution ICP-MS. High-resolution MS is important everywhere now, and it started to show that it's important in elemental analysis. With high-resolution ICP-MS, we will be able to analyze 300 elements plus stable isotopes. The idea is that every element is accompanied with around 3 isotopes. So if we have the periodic table that is around 100, If we gather with the isotopes, we are talking about 300 species. This is able to be analyzed with the high resolution ICP-MS. And this is the near future of our work in elemental metabolomics. And this is the far future. The far future is that we have a portable laser ablation ICP-MS, and we can point this laser ablation ICP-MS to a specific product, either it's a food product or any other product, and we can do analysis, and we can store in the results in the cloud, and we can use algorithms there, and we can compare with databases that are stored by Google, and we can define if the product is authentic. For example, if someone tries to sell you a fava santorinis, this way you will have a way to check about the trueness of the claim of the seller. And this is important, mostly in expensive food products. And this is the far future of elemental metabolomics. Let's summarize and show some applications of elemental metabolomics. Elemental metabolomics are to be applied in plant and environmental. And with elemental metabolomics, we can find association between genes and elements in plant tissues and their responses to the environments of the plant. That is the phenotype. We can access gene function that is related to genotype, and we can improve plant health. And we can also develop methods for determining the health status of plants. And this is also important. We can develop strategies for improved bioremediation, and we can work on the decrease of pesticides and herbicides. This is important for the environment and the humans. The point of elemental metabolomics that we are working right now is food and nutritional metabolomics. And this has to do with elemental compound profiles, and this has to do with authenticity. And I'm going to talk a bit later on about authenticity. And this has to do with biomarker detection for food quality or safety. And we can do complex toxicity studies, and we can define some food contaminants and their interactions. And we can see the nutritional and environmental effects on animal health, and we can monitor production. We can detect ingredients and processing methods. Important part for elemental metabolomics is clinical metabolomics. Biomarker discovery and new laboratory test development, the study of nutritional deficiencies and toxic exposure on human health, chronic diseases management, and delay prevention, and genomic proteomic basis of effects of elemental homeostasis. Here we can see an example from the accident we had in Fukushima. And the same thing it has with the accident we had in Ukraine, in Chernobyl. And this is how the contamination moved from the site of release to the human. And this is important, and we can, with elemental metabolism, we can follow this path. So this is one of the applications of elemental metabolomics. This is how we see elemental metabolomics and how elemental metabolomics connect food quality and safety screening of the population, environmental occupational element monitoring, and early disease diagnosis, personalized nutrition, toxicity and health effects, and all these things are being done through some databases that we have to develop, and we have to pay for that. Right now, we are in a consortium that is called Photomics.gr, and this is the national research infrastructure for the comprehensive characterization of foods. And this has to do, our contribution has to do with the elemental characterization of foods, and this through our current capability, that is ICP-MS. We have target analytes that are rare earth elements and actinides, ultra trace elements. Beyond them, between them are precious elements, trace elements, and macro elements. We are trying to determine three things: the origin, geographic origin of the food samples, genetic origin of the food samples, and production method. What's production method? Organic or conventional? Free range of farm products. Fish that are grown in fish farms or fish that are grown free in the ocean. And we are trying to investigate elemental authenticity markers, and we are trying to develop databases of elemental fingerprints of each product. And we are trying to see the possible differences with samples from other countries. And this is important for trade. So elemental metabolomics has an aspect that has to do with commerce. And this is also important. One of our ways of doing elemental metabolomics is also with fashion, with results from other analytes. Other analytes can be proteins, lipids, or carbohydrates. And this way, we are trying to improve classification rates. Elemental metabolomics has to do with food quality because we have to measure nutritive elements.
We have 5 minutes.
Okay, thank you very much. And also with food safety. And here you see some nice pictures from some publications we have from Fava Santorinis. We have developed elemental metabolomics methods for Fava Santorinis. And I can assure you that my students that were involved in this project were extremely happy to go there, because, you know, Fava is a special product of Santorini. So if you would like to sample, you have to go to Santorini. And that was the most important thing from this work. And we have done some other projects with honey geographical origin, and also with meat geographical origin, and milk and also the type of meat. And finally, I would like to mention my collaborators. All these things haven't been done by ourselves. We have worked with the University of Boston in USA, with the University of Belgrade in Serbia, with TMF faculty, as I told you, with Nazarbayev University in Kazakhstan, with the Ukrainian Academy of Science in Kiev, with Griffith University in Australia, Kumamoto University in Japan, and we have been working with the Institute of Quality Standard and Testing Technology of Agro-Food Products in the Chinese Academy of Agricultural Science in Beijing. And we have some industrial partners. Some are from the West and some are from China. And it's important, the last project that we would like to put forward, using some Bosnian byproducts. And this has to do with rare earth elements that are around in Bosnia. and we could use without purification, just as a food supplement or supplement in the ground, in the soil. And these are the conclusions. That elemental metabolomics is an exciting new subfield of metabolomics and links multiple domains and has numerous applications. I would like to thank you again for the invitation, and I hope that you will have some questions. And thank you very much for your attention.
Thank you, Professor Georgiou. We have only a little time for one short question. Any question? No. Thank you again for your very exciting topic on elemental metabolomics. And also thank you for sharing your memories for student days. Thank you.
Thank you very much.
Now, okay. Now we have sponsor presentations, which will be online too.
It will take, it will be online. It is the presentation which will be given by our sponsor, Zeochem do Zvornik, which is a branch company of the Zeochem in Switzerland. Anna, can you hear us? Anna, could you please unmute yourself? Anna, we can't hear you. Please press the unmute button.
Yes, can you hear me now? Hello?
Yes, we can. You can start.
Yeah, I was not allowed to do it before you give me the permission, actually. Yeah, good afternoon. My name is Anna Stojanovic. I am working in a company called Zeochem, which happens to be one of the sponsors of this conference. And I am kindly invited by an organizer to make an overview of the products in my company and their application in the processing industry. So I'll start my presentation. I'll share a screen in a moment. I cannot share the screen while other participant is sharing. So can Professor Georgiou stop sharing his screen?
Okay, thank you.
Thank you.
Sorry.
Okay, so as I said, I'm working in a company which is called Zeochem. It's a Swiss chemical company based with headquarters based in Zurich, and I will make a short overview of the products produced in our company. So the Zeochem as a company exists more than 200 years, since 1818. It is a family-owned company, and it belongs to big CPH group, which has a chemistry division, paper division, and packaging division. Chemistry division is called Zeochem, and today I will concentrate only on this part, and believe me, there is enough products there. So we have 4 different main categories of the products in our company, which are molecular sieves, deuterium labeled compounds, silica gels, and specialty zeolites. All these products are produced in the different production sites. One is produced in alumina in Zvornik, also at Ceochem DO Zvornik. Also, one part of the production is performed in the production site in USA, in Louisville, and we also have a production site in China and a small production facility here in Switzerland. So molecular sieves are highly active zeolite adsorbents. We have 6 basic types of these products. Type 3A, 4A, and 5A are actually the same type of the zeolites, where we just in 3A, we have a potassium form, then 4A is a sodium form. And
interrupt you, but we can't see your screen. Could you please?
You cannot see my screen?
Yes. Please start sharing.
Okay, because, yes, share screen. Sorry.
If you can press the stop sharing button and repeat again.
Can you see it now?
Yes, we can.
Okay, so I'm really sorry. So yeah, I'll just come back. These are the 4 different types of the products, which I said: molecular sieves, deuterium label compounds, silica gels, and specialty zeolites. And then I started talking about molecular sieves as the first type of products which we have in our company. And these are highly active zeolite adsorbents. We have 6 different types of compounds, while these first 3 types, 3A, 4A, and 5A are actually the same type of compounds, just with a different ion active, like a potassium form, sodium form, and calcium form, which are used for a removal of small molecules. And other 3 types of zeolites are used for a removal of the larger impurities and hydrophobic compounds, since they have a larger pores. So here I would like just to present now 3 most prominent applications of these products. So zeolite 3As are used in the natural gas processing. Natural gas must fulfill certain specifications before it can be further processed or sent to the pipelines. Specifications in the term of water content, CO2 content, and sulfur content. And Ceochem AG has a wide range of products to manage all these impurities in the most efficient way. And the majority of our products in this field have been developed in a close contact with the user and optimized for the high performance under real plant conditions. Another example is ethanol production. So ethanol can be produced from renewable raw materials such as wheat, corn, sugarcane, sugar beet. So in this process of production after fermentation and distillation, molecular sieves are used to further concentrate alcohol from 95 to 99.5 purity. Biggest market for these products are in the USA, South America, India, and China. And actually, Ceochem was the first molecular sieve manufacturer to introduce a molecular 3A molecular sieve for such application. And because of that, we are still owning more than 70% of global market share. And last application of molecular sieves, which I would like to show here, is application in concentrating industrial or medical oxygen. As you can imagine, because of Corona, this market exploded recently, and we have a high sales of this product because with the molecular sieves, you are able to actually concentrate the oxygen in industrial settings, but also in the cylinders which are used for a home therapy. So the core of these cylinders or concentrators are molecular sieves that are absorbing the nitrogen out of the air, concentrating the oxygen. Second type of products which we have in Telhem are specialty zeolites. So these zeolites are synthetic-based zeolites with a wide range of silica to aluminum ratio, available in spherical beads in a powder form. And since we can vary this ratio, we have different products depending on the application needs. And a basic application is absorbers of volatile organic compounds in the industrial application, odor control, odor remover additives in the formulations, such as thermoplastic, duroplastic, fibers, coating, but also very significant segment is personal care products, clothing, and footwear. The third class of a compound which we are producing in Telhem are deuterium labeled compounds. This production is purely done in Switzerland. It exists since 1970s when we started producing deuterium labeled compound as a standard solvent in NMR spectroscopy. In the meantime, deuterium label compounds showed some advanced properties in different application fields, and for us are important two market segments where we are quite active. One is deuterium labeled active pharmaceutical ingredients. This is like when this is the trend in pharma to use isotope label compounds, because it is proven that it helps the drugs to have a longer effects and also longer shelf life. And it's also at the same time, since we have a longer effect, we need to take less of a dosage. So it also decreases the side effects at the end of the day of drugs. And a few of our ingredients are now undergoing the clinical trials. Another segment is OLEDs, organic light emitting diodes. Telhem offers a large selection of deuterated reagents, and the focus for deuterium labeled OLEDs is on the blue color molecules, which is the most delicate component in this technology. And because the isotope effects results in a stronger bonds, the molecule have a significantly longer lifetime and very nice, brilliant, deep blue color. And the last, but definitely not the least, group of the products products which we produce in Telhem is silica gel. Silica gel is produced partially in Bosnia, partially in Switzerland. So raw gel is produced in alumina and Telhem DOO, and then is sent to Switzerland for derivatization. We have a three class of products called cell prep, cell beads, and cell spheres. Cell prep is irregular silica. Cell beads is spheroidal silica, but cell sphere is perfectly spherical silica with a very narrow particle size distribution. So here you can see how the silica gel production looks like. So this is performed in a very big 3 to 4 tons reactor, and where we have and this is the gel body after the aging, which we are now cutting and preparing for drying. After that, the silica gel is classified and, as I said, sent to for derivatization process in Switzerland. And in the right-hand corner, you can see our laboratory in Switzerland. And the derivatization is performed with the most standard silane like C18, CA, diol, TO, or something special, some special ones if we have a special requirements from the customer. So the main application of all silica gels, it is definitely chromatography. I mean, here on the right-hand corner, you can see the image of typical application, which is like a lot of application actually, starting from API and small molecules to biomolecules, proteins, and heavy metal scavengers. So depending on the application you need, you can come to us and tell us, and we can recommend you which type of silica, with which pore size and particle size you should use to obtain the best results. Of course, also which derivatization, which functional group. But there is a general rule that cell prep products, irregular silica, is mostly used in flash and preparative chromatography, while cell sphere spherical silica is used in analytic HPLC. So second application, for which we use our silica gel is beer clarification. For that, we can use actually lower grade silica, and silica is used for stabilization and clarification of a beer, which increases the shelf life of the products. Clarity is one of the most appealing characteristics of the beer that drives consumption of the products such as lagers and pilsners. And silica gel actually removes proteins responsible for causing the haze. And the last application which I wanted to share with you is the actually field in which we are focusing very much lately with the silica gel, is the separation of cannabinoids. Cannabinoids are of growing interest to the health and pharmaceutical industry, with more than 100 different compounds already identified. And high purity cannabinoids is actually possible to isolate only using chromatography. All the other techniques would give you a mixture of cannabinoids. And since pharma really needs always very pure compounds, we believe that this is next big pharma market for Theochem. And with this, I would like to finish my presentation. As I said, it was just an overview. If you have any further questions, comments, feel free to ask now, or also to contact me via email, which is provided here on the slide. Thank you for your attention.
Thank you.
Thank you.
Thank you, Anna.
Yes.
Are there any questions about products? Or no? No questions? Thank you.
Okay. Then wish you a pleasant lunch. I'm sorry I cannot join.
Okay. I'm sorry, Anna, you because you can't join us for a lunch. Now we have a break until 4 p.m. and we will continue then with invited lecturers. Thank you. See you at 4 p.m. parliamo di short film, non stiamo anche di
Jel treba ovo nešto uključivati ili ne treba? Da, čuje se. Hello to everybody. Good afternoon and welcome to the afternoon session. We have two talks today, and the first one is coming from Hungary. The speaker is Kinga Kutashi. Kinga is from the Institute for Solid State Physics and the Optics, Wigner Research Center for Physics in Budapest, in Hungary. Kinga Kutashi is a senior research fellow at this institute, and her main research interest is the applicability of low and atmospheric pressure surface wave microwave discharges in the fields of plasma medicine and plasma agriculture. Her work focuses on characterization of the discharge systems experimentally and by means of modeling and study the plasma, biological systems and plasma liquid interactions. So Kinga, please be welcome to start with your talk. The title of the talk is Surface Wave Microwave Discharge, a possible tool in plasma agriculture. Kinga is here.
Yes, I'm here. I try to share my file. Right. So I get trouble to share my screen. It offers me all kind of things, but not
Can you first open your presentation first, please? And the share screen after that. Just open your presentation first and then share the screen, please.
I have here my presentation.
Yes. And there is a green button. to share the screen?
I press the share the screen, but it offers me strange things.
When you press share screen, then choose your presentation and then click share.
But it doesn't allow me to choose the presentation. It gives me all kind of options like desktop and terminal unknown.
Is it your presentation opened?
Ah, Microsoft PowerPoint. Maybe I found it. Share.
Share. And now choose your presentation.
Okay, sorry. No.
Can you close your presentation and then open it again?
The problem is that it doesn't offer me to share. Now maybe, okay, maybe now it. Yeah.
Yes.
Yes, now it improved. Yeah, it was not offering me this option. It was sending me to different privacy places, so I don't understand why. So I'm sorry for this. Thank you for the presentation. In this lecture, I'd like to present the possibilities offered by a surface wave microwave discharge, and I'm going to focus in the examples on the plasma agriculture application. So when we talk about or thinking on using plasmas in agriculture, we can think on two things like direct plasma treatment of plants or seeds. And in the case of seeds, one important thing is treatment of seeds for disinfection of the seeds. And this can be done both at low and atmospheric pressure plasmas. The other point when we think in using plasmas in agriculture is the indirect plasma treatment, which means that we treat a medium like water, we create plasma activated water, and we use the plasma activated water to treat seeds and plants. Usually this can be done by using atmospheric pressure plasmas. So a sulfatron generated surface microwave discharge, it's very flexible because it allows the generation of plasmas both at low pressure and atmospheric pressure. So it can operate in a very wide pressure range from millibar to atmospheric pressure. Usually we generate the discharge in a small diameter tube, like 5 millimeter inside diameter tube in a flowing gas. And what sustains the discharge is a surface wave, which propagates on the boundary of the plasma column and the discharge tube. So this is a self-propagating, self-sustained surface wave which propagates along the plasma column. So the condition for this surface wave to propagate is given by this condition, which means that it can propagate if the plasma frequency is larger than the field frequency, and this term which includes the permittivity of the glass tube. The plasma frequency is defined by the electron density. So we are going to get a critical electron density above which the surface wave will propagate, and the propagation of the surface wave will stop at this critical electron density, which we see here at the end of the plasma column. So how this actually looks like, so we have a plasma column, and the electron density along this plasma column decreases to a critical electron density, after which it drops very fastly. And this region where the electron density is already zero, we call it afterglow. So this is the critical electron density. And the length of this plasma column is defined by the energy which the electrons can gain from the field, which is given here. And this depends on the collision of the electrons with the background gas. So this is the collision frequency. So the length of this plasma column will be defined on the gas what we are going to use, argon or air. And we will see in the continuation how this really influences the length of our plasma column. So what we can do with this surface and microwave discharge from the point of view of applications. When we are in a low pressure range, millibar range, we can connect this surface and microwave discharge with a reactor. So this is an argon, nitrogen, oxygen discharge. And what happens that we create different active species, atoms, molecules in this region, and the gas flow can carry these species into the reactor. We have this here on early afterglow region where we saw we don't have electron density. So this is more a recombination region. So here we start losing our species. And this, the length of this region is going to determine the density of species that enters in the reactor. What we see here, the light is coming from the NO2 molecules, and we see that it really fills up the reactor quite homogeneously. And here down we see another reactor which is much larger in size than this 40 centimeter diameter tube. So when we are creating our discharge in molecular gases, we have different reactive species. And these are the active species which allow us to use the afterglow for different applications. So we have oxygen atoms, molecules, nitrogen atoms, NO molecules, and also excited NO molecules, which give us UV radiation. So different applications rely on different active species. So in order to use our system, we need to be able to tune our afterglow to have the species which we want to use for the application. For example, for the sterilization, we want oxygen atoms and UV radiation. So when we are able to tune our afterglow, so to define different species concentrations in the afterglow region, this system also allows us to study different plasma chemical processes. So we can study the effect of different species on certain processes. So for example, degradation of the macromolecules, or we can use it for the nanoparticle formation. So how can we set the afterglow composition? So we are interested in this afterglow region, which is the reactor. We can do this by changing, of course, the initial gas mixture composition. So either we use nitrogen, argon, different mixture of nitrogen, oxygen, we will get different active species and different concentration of different active species. The gas pressure in the reactor, which is going to define us the absolute concentration, the gas flow rate, which carries the species from the discharge region into the reactor and also defines the homogeneity of the species distribution in the reactor, and the length of the early afterglow. So here was the early afterglow, which determines the density of species that enters in the reactor. So this is a recombination region, so we are going to lose our species. The longer this region, the more species we are going to lose. So this length of early afterglow, we can of course change by just moving the sulfatron up and down along this discharge tube. But what happens is that we are using in our system a gas flow. So it's a flowing system. This is a small diameter tube. And what happens is that the pressure in the different points of the system will be different. So we see a pressure drop from this point to this point. So by moving the sulfatron along the discharge tube, we are going to have different pressures. So the discharge is going to be generated at different pressure, which also defines the creation of active species in our discharge region. So this is illustrated here. So if we use 900 SECM gas flow and we have a 50 centimeter long discharge tube, in the reactor, we are going to have 2 millibar at the upper side of the discharge tube. We are going to have this pressure. So by moving the sulfatron, we see that we have different pressures, so the discharge is generated at different pressure. What we also see, as I mentioned at the beginning, that the length of the plasma column is defined by the gas we are using. So what we see here, that in the molecular gas mixtures, we have a much shorter plasma column. So when we are designing our system, we need to pay attention that when we use argon, we have a long plasma column. When we use nitrogen, oxygen, we have a short. So this also defines where we should put our sulfatron to have the same afterglow lengths. So what we see here, that just by changing the gas flow rate and moving the sulfatron, we can have different discharge conditions, different pressures, and also the length of the afterglow is different. So the species densities which enter the reactor is different. And again, if we use a lower gas flow rate, again, we have different pressures, and we need to move our sulfatron to a different position to have the same pressure as we had here. If we are using modeling of the system, then we can have an idea how all these parameters influence the species densities at the reactor inlet. So just for an example, we have here on argon, nitrogen, oxygen gas mixture, we have 90% of argon and 10% of nitrogen and oxygen. And we are moving from 10% of nitrogen to 10% of oxygen. So this is 0 nitrogen, and this is 1% of nitrogen, 10% of nitrogen. And what I'm showing here, just as an example, we can concentrate on the density, relative density of oxygen species. And what we see here, that just by moving the sulfatron along the discharge tube at the reactor entrance, we are going to have different oxygen densities for the given argon, nitrogen, oxygen concentration. And of course, when we change the mixture concentration, this is also changing. So how can we use this system in agriculture? We can study, so if we know by modeling, for example, how to set our system to have a cocktail of species in the reactor, we can study the effect of different species or the cocktail of the species on the seeds. And what we investigate here is infected seeds by Fusarium. So this is infected seeds infected with fungi. So what we see here, that using different gas flow rates, different gas mixtures, we can change the density of oxygen atoms in the reactor exactly at this point. So this is the densities calculated at this point where the seeds are placed in the reactor. The O2A molecules, which are also reactive, nitrogen atoms, NOx molecules, and at certain conditions, which is the nitrogen, 2% oxygen, we can also have UV radiation. So by changing the different mixture compositions, we either have just oxygen atoms and O2A molecules. If we add nitrogen, we will have also nitrogen atoms, NOx molecules, and at certain condition, we also have UV radiation. So treating the seeds at these different conditions, these are barley and maize infected seeds. These are the percentage of infected seeds. These are the control seeds. So we can concentrate only on the treated seeds. And what we see here that the infection is decreased mostly by argon, 20% of oxygen. So we can deduce that the oxygen atoms and the O2A molecules are very efficient in reducing the infection. And also when we add UV radiation, the infection is more reduced. However, in this case, the seeds are not germinating. So doing these experiments, we can have an idea which species play important role in the disinfection of the seeds. Going to the indirect plasma treatments, this system we can also use for creation of plasma activated water. And from our experiments, what we know that by applying plasma activated water to plants, we can increase their stress tolerance. So if the plants are stressed by certain conditions, for example, due to the climate change, they get extra stress. Applying plasma activated water can help to increase the tolerance of the plants against these stresses. So how can we tune the composition of plasma activated water with the surface wave microwave discharge in order to investigate which are those active species created in the liquid which has this effect of increasing the stress tolerance of the plants.
Just
so here yes?
A few minutes more, please.
Pardon?
Just to remind you to take care about the time.
Okay, I have just 2 more minutes.
Yes, thank you.
So here we see again the surface micro discharge, which we put in contact with the water. And how can we tune the composition of the plasma treated water? We can, during the treatment, we can change the distance between the water surface and the discharge tube and the gas mixture composition. So what we already saw that in the gas mixture composition, we get a shorter plasma column, and the electron density is decreasing along the column. So putting the water at different contact points, we get higher and higher electron densities. And in this case, the electron density is very low, but we have an afterglow, which is rich of active species. So the electron is going to influence the creation of hydrogen peroxide in our system. So higher electron density will give higher production of hydrogen peroxide, higher densities of nitrogen, NO2 and NO, which get in contact with the liquid and dissolve in the liquid, will give rise to higher nitrite and nitrate species in the liquid. And just going to my last slide, I show the composition of the plasma activated water, which is created at different plasma conditions, which means that we changed the composition of the initial gas mixture and the distance. And what we see here that we can get very different plasma activated waters. Here is the nitrite concentration as a function of hydrogen peroxide in the liquid, and the nitrate for the same hydrogen peroxide. And we see that we get very different mixtures using different conditions. So just the initial gas mixture composition in the discharge and the distance. And just showing that after 1 hour, our plasma activated water is still active. So we still have a high concentration of nitrite, nitrate, and hydrogen peroxide in the liquid. And thank you for your attention.
Thank you. Thank you for your nice presentation and talk. We are sorry that you missed our lovely venue and the place, and hope to see you here in 2 years. Köszönöm szépen, tanárnő.
Thank you very much.
Do we have some questions? So no questions now. Thank you. Our next speaker is coming from University of Zagreb, from Croatia. It is Anet Režek-Jambrak from Faculty of Food Technology and Biotechnology. And her talk is application of cold plasma in sustainable food processing. And my colleague will read the biography.
So we have Professor Anet Režek-Jambrak with us. She's currently at the Faculty of Food Technology and Biotechnology, University of Zagreb, in a position of full professor and scientific advisor in food engineering. She's also a leader of the Laboratory for Sustainable Developments. She spent part of her education in United Kingdom and France, and her field of research is food chemistry, food physics, non-thermal processing, and other areas. She's an excellent scientist, and she was awarded as a 0.1% of the world's best cited, highly cited scientists, which is an amazing achievement in 2019. And she also has got the national award from the Croatian Academy of Sciences. So we welcome you, Professor. Are we online? 1, 2, 3?
Yes, yes.
Excellent. Please give us your lecture.
Good afternoon to everyone. Thank the organizers for invitation. I will now share the screen. So please, do you see it?
Yes.
Okay. So everything should work for now. Okay, thank you very much for the invitation. I will speak today about the application of cold plasma in sustainable food processing. And about non-thermal processing technologies. So the first thing, what is the most important, is the aim of those non-thermal processing is to assure food safety. Of course, we have different electric technologies, also pressure-based technologies and mechanical technologies that we can consider as non-thermal technologies, and also non-electric technologies. The aim of sustainability regarding using those non-thermal processing is to show that those technologies can be considered as green or sustainable in terms of having low energy consumption, low emission of CO2, and also that we can claim that those technologies are cleaner, so that we can claim that this is cleaner production. So regarding food processing technologies, we have commonly used thermal technologies like pasteurization, sterilization, ohmic heating, microwave heating, also infrared heating, and opposite is non-thermal technologies like high pressure processing, pulse electric fields, high power ultrasound, pulsed light, ozonization, electron beam processing, oscillating magnetic field, and also cold plasma. So the main aim of those non-thermal technologies is to assure food safety, and also cold plasma application in food processing is relatively new. So I would like to say that this is a really necessity to consider the application of cold plasma in terms of agri-food processing. So from raw material, from field to plate. So we need to consider the application of cold plasma in agri-food processing. So the application of non-thermal technologies and also cold plasma needs to be focused on the application on bioproducts. So we don't have waste, but byproducts. And also to try to focus the research and upscaling of technology to the industry, regarding the lower energy consumption, lower emission of CO2, and also to use cold plasma, in example, for the wastewater treatment. The idea is to go toward circular economy and also to use everything in the circle, in the food processing chain, like water and also energy. And the idea is to afterward to claim and to label our product as clean and production that is cleaner. So also the aim is to consider zero waste processing. So where can we apply plasma in agri-food sector, in food? So the idea, we have different kind of examples where plasma can be applied. So this is application of plasma to obtain bacteria-free eggs. And also you all know what is the definition of plasma, so I will not talk about this. So we have different varieties where plasma can be applied on vegetable processing, fruit processing, and there is really a variety of different kind of application. So the foundation of electrical discharge is mainly focused on the invention of Nikola Tesla, where he discussed also the discharges in vacuum tubes. And we have the examples of the production and the production of plasmas. So where electrical discharge plasmas can be applied, so we have gas plasmas and the liquid plasmas. Gas plasmas can be applied, in example, on surface. We have production of active radical species, active molecular species, UV light, and also the presence of electric field. Also, we can obtain plasmas below water, so in water, so we have liquid plasmas. Also, we can obtain active radical species, active molecular species, intense UV light, electric field, of course, shock waves. And we also have a connection with ultrasound in terms of cavitation and microstreaming. So this is something that we have overlapping and in non-thermal processing. So the idea is definitely to use advantages of each non-thermal techniques. So in example, if we cannot use just one technique because of some disadvantages, maybe we can combine each technique and to have like a hurdle effect and the synergy application of non-thermal processing. Plasma is part of electrotechnologies in food processing, and the main characteristics is that the temperature of the processing is below 40 degrees compared to, in example, thermal processing, like pasteurization above 80 degrees and sterilization above 120. So the idea is to search and research of the possible upscaling of cold plasma in terms of inactivation of microorganisms at lower temperatures. So what are the possible mechanisms of the inactivation of microorganisms by using cold plasma is, so the proposed, we have 4 different actions that are proposed. So the first one is the direct destructions by UV irradiation, then shock waves. The third one is lipid peroxidation in membranes by hydroxyl radicals. And the fourth one is oxidation of DNA as a result of interaction with the oxygen radicals. So I would like also to stress the very important thing about plasma-induced stress in microorganisms. So we have also done the research with the plasma on different microorganisms. And we searched the recovery of the cells after plasma treatment, also cellular leakage, which indicates DNA damage, then biofilm formation, and also the influence of pH and generated peroxide radicals also on inactivation of gram-negative bacteria. And we have seen that in the first treatment, so in the first minutes of the treatment, we did the plate count, and we have seen that we have reduction of so 7.8 log reduction. And then after 18 hours, we saw that there was a recovery of 100% of initial microbial count. So this is something that can be like an obstacle, because if you use cold plasma in order to inactivate microorganism, we need to be really careful that we really did inactivated microorganisms. So they are entering in viable but not culturable state. So this is really important to be sure that there is no revitalization of microorganisms, and that we can be sure that we did obtain log reduction. That is really important. So as I said, these microorganisms are under stress. This was confirmed by catalase test, and they retained capability of biofilm formation in terms of salmonella cells. So they have recuperated, revitalized after 24 and 48 hours. And the results are showing great possibility of plasma application in industry, but with necessity of testing changes in microorganisms cell phase after this critical period, after 24 and 48 hours. So this is really important to achieve this sufficient log reduction, because this revitalization of pathogens can really present a great problem if classical heat and modern alternative techniques do not satisfy important inactivation requirements. Also, the application of cold plasma can be in terms of plasma activated water. So we have a great company, PlasmaLib from Australia. And Kinga told all about this plasma activated water, so I will not go into details. So the plasma activated water can be really applied in agri sector to obtain this better seeding of the seeds. Also, we have application of plasma treated air. We have also great examples of application of plasmas in agriculture and in the food cycle. So in this picture, we can see the impact plasma treatment of food using atmospheric air. Also, nowadays, when we have this COVID pandemic, we can stress the great application of plasma against viruses. And there are different kind of research about application of cold plasma in inactivation of viruses. So also we have now new publication regarding the application of cold plasma in inactivation of coronavirus. We have then different examples of the setup of cold plasma setup in terms of inactivation of viruses, and what is really happening in example on different kind of matrices. So we have different types of microjets present at picture A. Then we have the electric barrier discharge at picture B. And then we have various matrices inoculated with viruses and treated using cold plasma. So cold plasma can be efficiently applied on the inactivation for the inactivation of viruses. Also, we can use, in example, plasma to treat fruit juices, in example, to see what is the application of plasma in terms of preservation of fruit juices. So we have also done the research regarding the application of cold plasma treatment on pomegranate juice. And we wanted to see what is really happening with our setup and what is the efficiency of inactivation of microorganisms, and also what is the impact of cold plasma on preservation of, in example, vitamins and anthocyanins. So this can be really also a good, efficient application. We have done and finished our Green Voltex project in the end of February, and we used the high voltage electrical discharges for the extraction of bioactive compounds from Mediterranean herbs. And the main disadvantages, in example, of conventional extraction techniques are a longer extraction time, lower yields, a large amount of organic solvents, and poor extraction efficiency. So really, the application of cold plasma, so the high voltage electrical discharges can be in terms of higher yields, low CO2 emission, lower energy consumption, and we obtain faster extraction of bioactive compounds from cells, increase in diffusion rate, and we obtained mechanical destruction of plant cells. So in one sentence, we can say that application of high voltage electrical discharges can be considered as green extraction technique. So what do we consider as green extraction? So we discussed that we, in terms of sustainable processing and in terms of green technology, we need to think about reduced energy consumption. Also, we need to think about improvement of and optimization of existing processes, to innovate in terms of new equipment and innovate in processes and procedure. The idea is definitely to use cold plasma in extraction on bioactives from byproducts, in example from in agri-food chain. So we used a plasma generator produced by Impel Group from Zagreb, from Croatia. This is a really good instrument because we can control and optimize different parameters to optimize the process and to have higher yields of bioactive compounds from different Mediterranean herbs. So this was really a good example where plasma can be applied. So when we discussed about extraction and if we want to use non-thermal processing and in terms of sustainability, we really need to think about ecologic and economic way. So this is going to be something ideal because sustainability is really the impacting on three pillars: the economy, environment, and society. So regarding zero waste that I discussed, that I talked about regarding extraction, is the aim is to have higher extraction yield. The temperature of extraction should be lower, and also the aim and advantage of using high voltage electrical discharge is to have a solvent selection, so we can choose what kind of solvents we want to use in terms of green extraction. And regarding non-thermal sustainable processing, we think about circular economy. So we want to obtain a lower carbon footprint. We need to be in line with zero waste and to declare our product that is sustainable and declare as clean labor processing. This is the example where we did our experience with high voltage electrical discharge. And the idea of green solvents, so we used water, limonene, different kind of, so we use ethyl alcohol. We use also different kind of solvents by using Cosmo RS. So this is computer software when where we wanted to use solvent in example that is going to be able to so that our bioactive compound can be soluble in those solvents. The aim is to reduce the influence of pollution of solvents on the environment and also the creation of excess of CO2. And also we can optimize our treatment and the amount of solvent use and the volume of sample, in example, to have the optimum extraction processing. What is to conclude, what is really the mechanism of action of plasma? So the advantages of using plasma in agri-food chain is definitely the cell disruption in liquid samples that can improve extraction of valuable compounds through pores on cell membrane. So the electroporation, and this is a phenomena that is occurring due to electromechanical compression of membrane. And the aim is to extract and to protect bioactive compounds and, in example, essential oils through fast processes and using lower temperatures. Plasma occurs in the gas bubble at the tip of a needle in which there is an electron avalanche. So this is specifically a plasma discharge. And also we have different kind of phenomenon like the emergence of powerful dynamic shock waves. And also we have rapid expansion of plasma streamers. Also, there is the occurrence of free radicals and also pyrolysis, and due to occurrence of electrohydraulic cavitation. So this the production of free radicals can be optimized, of course. And regarding food samples, we need to also to be sure that we don't have excess of the free radicals that are present in the sample. And we can easily monitor this by using EPR, so electronic paramagnetic resonance, and the spin probes, because the aim is to have, in example, good extraction processes, but our extract needs to be nutritious and also radical free. So definitely we need to control the production of free radicals. So thank you very much for your attention. And I would like to say that the application of cold plasma in the future really needs to be interdisciplinary and together different kind of scientists working on application and definitely on the scale up to industry. Thank you very much.
Thank you, Annette, for presenting us the novelties in the field of green and sustainable chemistry processes. Do we have any questions from the audience? No, so yes, we have one.
Annette, thank you very much for wonderful presentation. I'm Susanna from Banja Luka. I would just like to know a little bit, I was thinking all the time about free radicals when you were speaking. So how do they manage this or whatever? But you nicely explained that, of course, you are paying attention on this. I just wonder, do we have groups somewhere around Europe or the world who are working on the devices which would be able to continuously measure the concentrations of the free radicals within this process in order, of course, to control it, as you mentioned? Is there any progress in this area, sensors for free radicals, let's say it simply?
Yes, yeah, definitely. We were having a collaboration with our colleagues from Canada, and also we discussed about different kind of sensors that can be inserted inside of a reactor where we obtain high voltage electrical discharges. And well, this is really tricky because those sensors needs to be in the electric field. So we need to be sure what is going to happen with those sensors. Also, we want to use electrical discharge in the liquid. So we need to have like sensors above the liquids, because this can be, so we can destroy those sensors. But during our project, we also collaborated with different kind of scientists all around the world. And we have good connections with scientists from Germany, from Ireland. In example, Professor Schlitter from Institute in Potsdam. So they're really doing a great job on application of plasma in food. Also, Professor Tivari from Ireland, from Chagas Institute. So we also did the joint collaborative project on the monitoring of the production of free radicals in the water and inside of the fruit juices. So also this is something that is really very tricky, because free radicals are very fast reactive species. So in a few seconds, so you can have it during your process, and afterwards they will, in example, join with the first organic molecule in the matrix. So this is really important to be like, in example, with the method like electronic paramagnetic resonance, or ESI, EPR, ESR, what is the abbreviation. And you can use, in example, spin probes. So the idea is to capture free radicals. If you want to monitor and to quantify what is the really production of free radicals inside of your liquids, in example. And the idea, if you need to transport your samples, you need to cool it down, so with liquid nitrogen, so to stop the chemical reaction. And also different kind of using of EPR on, in example, solid foods can be also easily applied. There is a group in Copenhagen, in University of Copenhagen in Denmark, where also our friends and colleagues from Spain, they did the research about really formation of free radicals by using the different kind of non-thermal techniques. So definitely this is something that should be monitored in terms to assure food safety, and definitely to say that we have like food safe product. So we can easily talk about this for an hour.
For a coffee break now, but not unfortunately. So thank you once again. Thank you.
Thanks. Thank you very much and have a nice afternoon.
Thank you.
So we have a great pleasure today to greet our industrial partners and colleagues who are, as I understood today, supporting this conference. Colleagues from Alumina company. It's going to be Jay Kostic, isn't it? Okay, so Jayko, you will update us a little about Alumina's activities in recent months and years. The floor is yours. Microphone, you will use the portable one.
Yeah, I think it's, is it working? Can you hear me?
Excellent.
Yeah. Hello, everybody. My name is Željko Kostic, and I'm coming from company Alumina, DOO, and now it's working. And I will give you a short presentation about our company, what we do, what is our strategy, how we cooperate with universities, and how we use science in industrial way. And I'm glad that our company is continuously supporting university, especially Faculty of Technology in Zvornik, and continuously supports these kinds of conferences. So our company, Alumina DOO, is located in Zvornik, and this presentation is made mainly for our customers. So I'll make a short connection between, I will emphasize the connection between university, or actually Faculty of Technology in Zvornik and Alumina during this presentation. And our company is connected to railways and roads with ports in Adriatic Sea and Danube. And at this moment, we have approximately, actually, we have more than 1,500 employees, and which is about a quarter of work totally employed in Zvornik municipality. Short history, we have started production officially on 6th of October in 1978. And we were mainly producing metallurgical alumina, which means producing alumina for production of aluminum. Somewhere in the 90s, we have started the production of zeolites for detergent grade. We have survived the privatization in the period of 2001 up to 2011, actually 2013, and then in 2013 the government took the ownership of the company. This slide shows you how we are organized. We have, since we are a production-oriented company, we have production sector of all productions. Then we have maintenance, all different kind of maintenances. Then we have we need to sell the products. So we have a marketing sector, commercial sector, logistics sector. Of course, we need to have a R&D sector and quality control sector. In order to organize people, we need to have sector for general affairs, HR sector, and of course, financial sector. Also, we have sector for integrated protection and sector for investments. Regarding our product profile, Here we are coming to the point that I need to express again and point out the connection between real sector and universities. In our case, it's a Faculty of Technology in Zvornik, because with their help, we developed most of our products. Of course, in the beginning, that was alumina mainly for metallurgical uses, but then we developed different other types of non-metallurgical and white alumina. Also, we have in our product portfolio aluminum hydroxides, different grades, wet, dry, white, milled, fine precipitated. As I said earlier, we have a production of zeolites, LTA or Linde type zeolites, and special other types of zeolites, special zeolites such as ZSM5 and mordenite. And in order to produce zeolites, we needed to have water glass in our product portfolio. And recently we have started the production of silica gels. The next slide shows the main application of our products. As you can see, we are covering pretty much a lot of different productions. So our products are used for productions of detergents and molecular sieves, mainly zeolites, flame retardants, aluminum salts, mainly are aluminum hydroxides, and aluminas for aluminum, of course, cements, refractory, etc. Currently, we are products, actually projects that are in development. Sorry. Where's the? So we are producing different grades of aluminum hydroxides, dried and milled already. Then we started the production of silica gels and special grades of zeolites, fine precipitated hydroxide, as I said. And this year we will start the project for corundum, production of corundum. Also, for the future, this is not working now. I spent the battery. For the future, we no, the next slide. Next slide, please. Stopped. Znači radi samo. So for the next project, we have in plan to produce Faujacid zeolites such as zeolite 13X and Bemite, and to produce fine milled hydrates. So when we use the science and produce the products, we need to sell them. And for that part, this slide shows what other people, other than scientists, do. So we are selling our products to more than 100 customers in 44 countries. And we have more than 40 years now in experience in alumina production and more than 30 years in zeolite production. And this map shows where do we sell our products. Here are some of the main users of our products. Probably most of you know the Procter & Gamble, Henkel, Reckitt Benckiser, Saponia for production of detergents, MOL from Hungary, Talon from Slovenia, Feralco, etc. When after the bad privatization, our management decided to change the portfolio. So we switched from metallurgical grade alumina toward non-metallurgical grade alumina and more special products. And in this sales trend, you can see from 2012, this red is a metallurgical grade alumina, zeolites and hydrates. how our sales trend switched. We slowly switched toward the non-metallurgical uses of our products. And as you can see, zeolites also grow, alumina for non-metallurgical also grow. And in 2020, we didn't produce any of alumina for smelter grade, for production of aluminum. We still can produce alumina for, if the price of aluminum goes up and the price of alumina goes up, we will produce it. So we need to adapt toward the market in order to survive. Also, the strategy here shows how our revenue trend goes up. This is Corona. This gives us this shortage. And this year we are planning to be somewhere here again. So we slowly get the equilibrium. We stepped, this is the step that we made. And also this shows that industry was not as much as affected as it was some other services in our society. Again, these next 3 slides will show you how our market share for all products, alumina, zeolites, and hydrates. This shows the strength of alumina because we have so many clients. And then when in earlier period we had only one client, or we were like supplier for 100% of one customer, and this shows how we share the market in a way that if one client goes down, we can survive. I'll go fast so you can see that where do we export alumina, hydrates, zeolites. These zeolites are the most spread and have the best position in our products. So this slide shows why are we stable. Accounting the fact that the science gives us what to produce, we have our raw materials from local deposits. All our bauxites are coming from Bosnia and Herzegovina, Montenegro, neighboring countries. We have our own power plant. So coal is coming also from Bosnia and Herzegovina, gas from Russia, of course. Then we have our own workshop and maintenance. This is also great power to have and strength. Also, we have internal storage for raw materials and products, so we can strategically sell the products when the price is the best. And because of this, we have a stable market, of course. And the other fact is that thanks to Professor Vucelic, I would say, we are the only producer of zeolites in the world that is producing commercial zeolite directly from the bioliquor. And of course, I have to thank two other professors, which is Professor Lazic and other professors from Faculty of Technology in Zvornik, because they also had a great impact of our product portfolio. So our philosophy is to continuous attention to achieving a high level of service performance with specific focus on products availability and the delivery assurance. Conduction of business according to the requirement of our customers and achieve the highest quality standards. Open and transparent relationship and negotiation with all our suppliers. Maintenance of high ethical standards in external and internal relationships is essential to maximum success. Constant development of new products every 6 months. Thank you.
Thank you, Jacob, very much. Please stay on board. Dear colleagues, would somebody like to ask some curious questions about Alumina?
Yes.
Jacob.
Mr.
Please, go.
You have mentioned that you are producing ZSM5 zeolites for monazite and silica gel. Is this something that you have developed with some professors or maybe with some company?
Yeah, I forgot to mention, if you go back a bit, please, one slide. We are constantly talking and with our partners. I forgot to mention our greatest partner, two greatest partners actually, Geochem DOO and Silchem, because thanks to them, we developed the products that Mr. Petkovic asked, and thanks to them, we transfer the knowledge and to Zvornik. So we have production in Zvornik instead of Switzerland. And also, same thing happened with the factory in Hungary. We transported the production from Hungary in Zvornik also, regarding the fine precipitated hydroxides. Yes, we use the technology that they had, but also it's not the same as the cutting of I don't know, 1 meter length of the metal plates. It's a bit complicated.
Maybe we can say a few words. You mentioned that you support the Faculty of Technology, but I must thank in the name of my colleagues from the Faculty of Science in Banja Luka that you also do support us, and really we enjoy incredible collaboration in recent years. Especially your support in analytical techniques is really important for our graduate students. But I would like to add what we learned from these few months, a few years, I can say already. What we learned about Alumina is that the strength of this company were her people. The people who kept her alive. I must also admit that there are veterans like Professor Lazic, inventing engineers who did wonderful inventions in the past, who gave you strength. And you kept this spirit with generation of Professor Lazic really somehow developed within the factory to keep the factory as your own home. And this is a unique situation. And I just want to tell you, there is a wonderful research now going on in Banja Luka, Faculty of Political Sciences, about you. Oh. Yes, we have a PhD student, Miss Angela Pepic, a wonderful researcher. We collaborate with her very much. She's looking at your company as a unique example in the world, because you were the only company which were privatized in a bad manner. As you said, you had problems with privatization. You were robbed, we can say openly that. And you simply raised it from the ashes thanks to your people, the strength of your community. You kept the factory alive, and that's why you're now a giant. So we're looking forward for Angela's paper about you. Yeah, thank you, Željko, very much. We are out of time already. So, dear colleagues, we will go to the poster session to relax a little, and the colleagues online can follow the poster sessions online as well. So we thank Željko again.
You're welcome.